The following message is best viewed on an oscilloscope.
Welcome, everybody. Hi.
Hello.
So, hello. It's I think it's 8:25 at Seoul time, European time, and here is 3:25 in Asia. I'm in Korea, and I'm doing the chairman of this session, and I welcome everybody. We have right now 19 people, including the host and the two convener. So we actually have 16, so we can wait more. But since our agenda is quite, the fixed one, we have to start anyway. So maybe more people will come. So you have two in this morning session. We have two talk. One is Soham Bhattacharya. They both, and Seungjin Yang, they both talk about the top-quark and top-quark physics using machine learning and some the artificial intelligence or whatever. So we will have then the 10 minutes general discussion session. After that, coffee break. And the time, the thing I have to let you know to speaker is we have 25, I mean, you guys have 25 minutes, but 18 minutes talk and 7 minutes discussion. So I'm gonna interrupt you very briefly, very shortly at 18 minutes later. So let's first call Soham Bhattacharya for the boosted top tagging and measurement of boosted top polarization using jet imaging. Soham, are you ready?
Yes, let me share my screen.
Okay. Go ahead.
Do you see my mouse also?
Yes.
Okay, fantastic. Okay, so hi everyone. I'm Soham. Thanks for letting me deliver the opening talk of today's of this session, and I'll be talking about the use of jet images for detecting the polarization of top quarks and also for tagging top quarks. So in standard model, whenever top quarks are produced in pairs in TT bar production, the top quarks are not polarized because of the vector nature of the QCD couplings. Whereas on the other hand, when there are single tops being produced, the top quarks are all left-handed because of the V minus A nature of the TBW coupling. So any change to the structure of the interaction, this will lead to a change in the polarization of the produced top quark. So for example, I've given two processes here. You can have stop quarks decaying to top and chi10, and the coupling is given by this expression here, and the form of GL and GR, this will determine the polarization of the produced top quark. And not just that, even the composition of the LSP, which is chi10 here, whether it is Bino, Wino, or Higson alike, that will also determine the polarization of the produced top quark. Then you can also have heavy W primes decaying to top bottom quarks, and that interaction is given here. And here also the value of GL and GR, this will determine this will determine the polarization of the produced top quark. So GL and GR can lie between -1 and between 0 and 1, and whether it is fully left-handed or fully right-handed, and that will be the polarization of the produced top quark. So here's an example image for a W prime mass of 3 TeV from this reference given here, decaying to top and bottom. And you can see that in red and blue, the fraction of the energy carried by the B quark produced from the top decay, that depends on whether the produced top is left-handed or right-handed. So the kinematics of the top decay products can be used to differentiate between the polarization of the produced top quark. So we can use the polarization of top quarks because it serves as a promising window for exploring the nature and the existence of new physics. Because just as we saw, we can explore any deviation from a standard model by measuring the polarization of the top quark that we detect in our data, that we record in our data. And the measurement of this polarization of highly boosted top jets in colliders, this can be quite challenging because of the very busy environment. And several studies have already explored different kinematic variables for this purpose. For example, this ZV, which I have shown here. But in these slides, I'll be describing the use of an image-based CNN or a convolutional neural network for detecting the polarization of both hadronic and leptonically decaying boosted top jets. And I'll also be showing the tagging performance of this CNN based on our images, focusing on the leptonic decay modes here. And this is a work in progress, and will be archived very soon. Okay, so a brief introduction to top polarization before going into our study. The angular distribution of the top decay products in the top rest frame is given by this relation given here. Here, the F stands for the different particles, for example, the fermions or the W in the top decay. The P0 is a polarization of the top and can lie between -1 and 1. The theta F here is the angle between the fermion or the W and the top spin direction in the top rest frame. And Kf is something called the spin analyzing power, and this is physically this is something like how much, for example, the du, b, or the w particles are correlated with the top spin. The more they are correlated, more is their spin analyzing power. And the values of Kf for the different top decay products are given here. So for left-handed hadronically decaying top quarks, you have P0 equal to -1. In this case, one can work out from this relation that the B and U quarks are more likely to be aligned with the top spin in the top rest frame, and hence more boosted in the lab frame, and hence in the lab frame they'll be less separated. As for right-handed top quarks, for right-handed hadronically decaying top quarks, the D quark is more likely to be aligned with the top spin, and hence more boosted in the lab frame. So in this case, the B and U quarks will be not so boosted and held, and hence more separated in the lab frame. Similarly, one can also deduce that for leptonically decaying top quarks, the B quark will be harder for the left-handed top quarks, and for right-handed ones, the lepton will be harder. So the kinematics of the top decay products from left and right-handed top quarks, they will differ, and one can exploit this feature, which also appears or shows up in the jet images of the top quarks. So before going into the more details, I'll just present a few technical stuff about the work. So we have considered a few benchmark processes. We have a stop pair production, where the stop is of mass 1 TeV, and the stop goes to a top neutralino, and the neutralino is of mass 100 GeV. We have a heavy W prime of mass 3 TeV decaying to a top and a bottom. We have top pair production and a QCD production, where we apply a PT hat min of 400 GeV, which is the cut on the produced quarks in order to have boosted jets. For the simulation, we use MADGAR5 and also MAXSpin to properly simulate the spin or the polarization of the top quark. followed by hadronization using PTI8, and we use Delphis to simulate the detector where we use a CMS card. For the jet formation, we use anti-KT jets of radius 1.5, and we apply a soft drop with Z cutoff 0.1 and BT equal to 0. On these jets, this choice helps to clean the jet of both soft and soft collinear emissions. And following soft drop, we apply a jet PT cutoff 200 GeV and eta less than 2.4. And you can find some more distributions in the backup. Okay, coming to a network structure. So for this study, we use a network which is essentially based on the widely used LHeNet CNN, which is shown here. So we essentially have 3 convolution layers, which are shown in the cyan layers here. And following that, we have a fully connected layer, which is then combined using a sigmoid to give an output. So we have tweaked the network parameters, for example, the number of channels, kernel size, number of nodes, etc., to obtain a reasonably good compromise between the performance and the training time. And we have also checked the performance improvement offered by a few other networks. For example, we have checked that the improvement offered by GoogleNet is quite small, but the training time is quite higher. This is mainly because that jet images are relatively simple and coarse. For our study, we use 50 cross 50 jet images. I'll come into the details later. And a simple network is usually able to learn most of the jet image features. And for our purpose, the input to the network has 3 channels corresponding to the 3 jet components, which we divide into tracks, photons, and neutral hadrons, which are the Delphis outputs. And this improves the performance for electronic top tagging and also for the polarization detection. Okay. So some details on how we form the jet images, or what we call the pre-processing of the jet images. So first, we do something which is a mass rescaling and a Lorentz boosting. This follows the technique described in this reference here. So we scale the jet for momentum such that its mass is mb, and the jet is then Lorentz boosted to a frame in which that its energy is eb. So the ratio of these 2 parameters, or mb or eb, what we call gamma b, is what is important and not their absolute values. The reason we do this is to obtain an image where the components are fairly well separated irrespective of the boost of the top. So if we boost to an image, so if we go to the top rest frame, for example, where gamma b is 0, you can see this lower right plot that the 3 subjects of the hadronically decaying top, they are pushed to the periphery of the image, because in the top rest frame, the 3 subjects are recoiling against one another. So this does not offer a very good discrimination power. So we have to choose an optimal value of gamma b where the 3 subjects are, or 3 or 2, depending on the hadronically or leptonically decaying mode, they are well separated. And we have seen that gamma v is equal to 2 is a fairly optimal choice. And after this rescaling, we do a Gram-Schmidt transformation. So what this essentially does is you go from the lab frame, which is this XYZ coordinate, which is shown in the lower left diagram, to this epsilon 1, 2, 3 coordinate. So this says that the jet image now lies in the plane which is perpendicular to the jet axis, which is this gray shaded area shown here. So this helps to separate out the components better. So if you don't do this, for example, you will see a jet image like the top image that you see here, where this is a hadronic top jet image, but you don't see any kind of feature because you don't do this transformation or rotation. And I'll not go into the details of this transformation here, but I can come back to this required. And a jet image size is 50 cross 50, and the color axis here, this is the constituent energy divided by the jet energies, or the energy fraction. Okay. Now, so here are a few example jet images. In the top row, you see the hadronic top jet images, and in the bottom row, you see QCD jet images. These are divided into 3 components: tracks, photons, and neutral hadrons from left to right. And you can see a clear distinction between hadronic and QCD jet images. You have a hard lobe on the right for hadronic top jet, and a wider blob on the left-hand side, corresponding to the other subjects in the hadronic top decay. Whereas for QCD, the left-hand side lobe is much softer because it is mostly single jet for QCD jet. You can have some components coming from emissions which show up in the softer secondary lobe. Coming to leptonic top versus QCD, here you also see a very good distinction between the leptonic jet images and the QCD jet images. The lepton offers a far more cleaner signal, and hence you see that the two lobes are far less connected in the leptonic scenario compared to the QCD scenario, where the two lobes are because of the color connection. Okay, so coming to the top tagging performance. So I focus here on the leptonic top tagging, and this has been trained on jets from TT bar versus light quark jets from QCD. And you can see this blue solid line here, which shows the performance when evaluated on the TT bar sample. And in the blue dashed line is the performance of the leptonic top tagging when we evaluate the same training, which was trained on top pair sample on the W prime 3TV sample. So they are fairly comparable. So the CNN does perform quite well when it comes to leptonic top tagging, giving us a background efficiency of only 0.01 to 0.02% at 40% signal efficiency. And the main important feature of this is that this image-based leptonic top tagging, this is independent of lepton reconstruction ID, which can be quite challenging in highly boosted top jets in colliders. Okay, then I move to the polarization aspect. So here on the top row, I have the hadronic top jet images for left-handed top quarks, and in the bottom for right-handed top quarks. And you can see some differences between the two. The amount the two lobes are connected, that depends on whether the top is left-handed or right-handed. This is simply because what I said earlier on which quark is more boosted and hence more or less separated. So one can use this feature to differentiate between left and right-handed top quarks. So we train this on left-handed and right-handed jets from stop pair events, and we compare it to a kinematic variable called cos theta star. Cos theta star is essentially the cosine of the angle between the top jet in the lap frame with respect to the D-like subjet in the top rest frame, and the distribution for left-handed and right-handed top quarks is shown in the upper right here, and you see that cos theta star offers some amount of discrimination, as has been shown in this paper referred to here. You see the output of the CNN for left-handed versus right-handed hadronic tops on the lower left. And here you see that, okay, so for the left-handed, it's in red, and for red solid, and for right-handed, it's in red dashed from stop pair. And if you evaluate this on a W prime 3TV sample, the lines are in blue. One estimate of the performance difference between the CNN and the cos theta star is their ROC, where the dashed lines show the ROC obtained using the cos theta star variable, and the solid lines show the ROC obtained using the CNN variable, and you see that the CNN variable does outperform the cos theta star. Now coming to a better estimate of the performance difference, we go to a physically measurable variable, which we call the asymmetry. So the asymmetry is simply given by this definition of A, which is the asymmetry for a given discriminator D. D can be the cos theta star or the CNN variable. You calculate the number of top jets passing the cut D greater than C minus the number of tops passing the cut D less than C, divided by the total number. So this tells you the asymmetry of the distribution, and the composition simply refers to whether the top is fully left-handed, fully right-handed, or somewhere in between. C is an arbitrary cut on the discriminator, and one can change this to check the optimum value of C. And so the distribution of asymmetry for the cos theta star variable for the two extreme compositions, fully left-handed and fully right-handed, are shown in these red lines here. The red solid line shows it for the fully left-handed case, and the red dashed line shows it for the fully right-handed case as you change the discriminator cut value, which is in the x-axis. And similarly for the CNN, it's shown in the blue lines when you between the two different compositions, left and right-handed. So what we want to measure here is the maximal change between the left-handed and right-handed scenario. So the difference between AL and AR, this maximal change is a measure of the sensitivity of the discriminator D to the composition and hence the polarization, because the polarization affects the composition of the top jets that you will see. And you see that this difference for the cos theta star variable is this red dotted line, and the difference between these asymmetries for the CNN is in the blue dotted line. And you can see that the maximal change offered by the CNN variable is much larger, almost a factor of 2 compared to the maximal change that is offered by the cos theta star variable, which shows that the CNN is far more sensitive to the polarization of the top quark or top jet compared to the kinematic variable cos theta star. Okay, now I come to the last section of my talk, which is the leptonic top polarization. So similar to what I showed before, here are the images for leptonic tops from left-handed top quarks on the top, and for right-handed top quarks in the bottom, divided into 3 components of the jets, which are the tracks, photons, and neutral hadrons. Now, if you recall from the formula that I shown before, for left-handed leptonically decaying top quarks, the B quark will be more boosted, and for right-handed ones, the lepton will be more boosted. This can be seen in these images here. For example, in the lower left plot, you see that the right-hand side blob is harder than the one on the top. This is because the lepton will essentially be a hard track. And for example, in the image of the neutral hadrons, you can see that in the top plot, the right-handed blob is harder because the B jet here is harder compared to the compared to what you see in this lower right plot, where the lepton is harder and you don't have any significant contribution from neutral hadrons here. So
you have more minute.
Sure, I'm just near towards my end. So one can use this to train to make the CNN learn these features. And similar to that, we have compared to this, we have compared the performance of this with a kinematic variable called ZL, which is the lepton energy fraction in the top jet. And you can see their ROCs here. So in the dashed line, you see the ROC obtained using the ZL variable. And in the solid line, you see the ROC obtained by the CNN. And you can see that CNN does outperform the ZL variable. And also the CNN is independent of lepton reconstruction ID, unlike the ZL variable, which needs some form of lepton reconstruction. And similar to before, here's the asymmetry plot. And even here, you see that the maximal change in the asymmetry for the ZL variable is the red dotted line, whereas for the CNN is the blue dotted line. And you can see that the CNN discriminator is about 1.3 or about 30% times, about 30% more sensitive to the change in the polarization compared to the ZL or the kinematic variable. So this brings me to my summary. So the polarization of top quarks can serve as a very powerful tool in the search for new physics. And we have shown that the leptonically decaying boosted top quarks can be well tagged by a jet image-based CNN. And this is free from the issues which come with reconstructing and identifying isolated leptons in a highly boosted top jets. For the polarization, we have measured the polarization of both hadronically and leptonically decaying top quarks, and we have shown that the CNN-based result that performs better than the standard kinematic variables like ZL and cos theta star. And these image-based techniques are very importantly free from issues with lepton reconstruction in boosted jets. So that brings me to my end, and this work will be archived very soon. Thank you very much.
All right, thank you so much, Soham. And it was wonderful talk, actually very interesting. And looks like the CNN is very promising for the top physics compared to the conventional one. So we have, I think, we have more than 3 minutes left since we started 2 minutes later. So are there any questions for Soham? Raise your hand. Yes, Yoon. You can turn on your microphone.
Can you hear me?
Yes.
The page 1, there is the solid line and the dashed line. And could you explain what's the difference?
Sure. So the dashed line is that obtained at the partonic level, whereas the solid lines is after hadronization. So you see some deterioration in the separation using this variable following hadronization, and following detector effects, the power of this variable gets even worse.
That answers Yoon.
Thank you. If you don't mind, can I have another question?
Sure. Why don't you go on?
Could you tell me how much events you generate? There is no information to the sample size.
Yes. So it is roughly 1 million.
Each one.
Yes.
Okay, thanks.
So each one means the test sample and
okay. So we have
sample.
about 1 million, say about 1.2, 1.3 million, and the training sample is roughly 800, 900,000, and the rest is about 200K. Yeah, similar.
All right.
200, 300K. Yeah.
Good. Are there any questions?
Yes. I'm sorry, Inky.
Yes.
I have a time raising my hands. I don't see how to do this here. So if no one else is raising the hand, maybe I ask a question.
Sure. Go on. Yeah.
So actually I've got two, but the first one is related to the method that you are mentioning in this interesting talk. Soham, let's see if I can point you to the page I'm interested in. It is related to the intrinsic definition of your method. So let's say page 6, when you say that you have 3 jet components, tracks, photon, and neutral hadrons. I mean, in order to apply this in our analysis, it means that we need to be able to separate these 3 components from the experimental point of view, right?
Right.
So it means that we need to have knowledge about tracks, and this we usually do at a fairly precise level. Photons, which, I mean, I assume you're talking about all the photons that are produced, even in the shower, predominantly. And then there's the most challenging and most difficult part, which is neutral hadrons. Neutral hadrons are really difficult to measure. I mean, to identify all of them, right? Pi zeros to photons, lambda zeros, neutrons. Neutrons are really hard to measure in the sense that you see them only indirectly because they don't leave any charged track in the shower and the hadronization. So you're assuming we're able to separate these 3 components rather well. Is that a fact?
No. Okay. So for this one, what we have done is we have taken the 3 different the 3 different components that Delphis gives us. But to apply it in a real experiment like Siemens class, we don't exactly need this. So we can measure tracks very well. So we can have tracks. And for the other 2, we can have the energy component of the jet deposited in the ecal and the energy component of the jet deposited in the hcal. And for neutral hadrons, for example, for pi 0, that will essentially be entirely ecal. And the neutral hadron, the neutral components deposited in the hcal, which are not massed to tracks, that can be counted as the neutral hadronic components. So we need I mean, we get better results if we divide it into these tracks, the equal component and the hadronic component, but we don't need exact precise ID of photons or IDs of the IDs of neutral hadrons.
Okay. By the way, I mean, we have another discussion time after the session before the coffee break. So if you have more questions, I mean, we can go on in the discussion time. And for a while, I mean, Soham, thanks again for your nice talk. And let's move on for the next talk. Seungjin?
Yes, can you hear me?
Yep. Can you turn on your camera and share your screen slide?
Okay.
If possible, I mean, you can turn on your camera.
Yeah.
Good, great.
Hi, my name is Seungjin Yang, and I'm a PhD student at the University of Seoul. I will talk about the top-quark pair reconstruction using an attention-based neural network, and I prefer to call it zero permutation jet pattern assignment. When reconstructing the events with intermediate state decaying to jets, we need to assign jets to patterns. And as the number of jets increased, the jet pattern assignment problem became more difficult. So we introduced the self-attention for jet assignment network called SAJA without requiring jet permutations. And we test the performance of SAJA in the fully hadronic top-quark pair production events. Here are the examples of the existing jet pattern assignment method. The first and second, the kinematic fitting, which is a very traditional approach. And third is machine learning approach. And recently, people are trying to apply machine learning to jet pattern assignment problem. They just train a binary classifier to predict whether the assignment is correct or wrong. Although the specific strategies are different, but this method follows the same three steps. Firstly, they compute or promising jet permutations, and each permutations is the jet pattern assignment candidate. And then they evaluate how well each permutations agree with the underlying event topology using chi-square or likelihood or the sigmoid of neural networks. And then they choose the best permutation. And a common problem with this method is the combinatorial explosion of the number of permutation with the number of jets. So we translate the jet pattern assignment problem into a jet-wise multi-class classification task. This equation shows the form of our neural network, which is very general multi-object classifier. FCC-eh is deep learning model with weight theta, and XJ, the reconstructed jet variables, and Y indicate the labels. And since it is hard to distinguish jets originating from T and jets originating from anti-top, we introduce arbitrary indices 1 and 2. And also there is a special class other, which indicate additional jets produced in the event. There is no explicit constraint on the model output. So it can be possible the output of neural network is different from the underlying event topology. Such event said to be topologically invalid. And in the case, we veto those events. But there's one problem. Since the indices 1 and 2 arbitrarily, we cannot give the truth label to our model with the usual objective function, so-called the loss function. So we define a new objective function in the following way. The idea is very simple. We compute the objective function for each of the two combinations, first assigning T1 to the gel level top quark and T to the anti-top quark, or second with the T1 to anti-top quark and T to the top quark. Then we choose the one with the lower loss value. I wanted to emphasize that arbitrarily neural network architectures, such as ConvNet, graph neural network, or recurrent neural network, can be zero permutation, zero pattern assignment model in the inference time. Among the various types of neural network architecture, we choose to use a transformer, which is the neural machine translation model, and it features self-attention. Self-attention is just a weight sum of the elements of the input set, where the weight matrix is also computed from the elements. And self-attention based model can learn the dependency between elements. In our case, the events correspond to the input set, and Z correspond to the element. And the bottom figure shows the self-attention weights in the English to German translation task. And I hope this figure gives you some insight. And here are the architecture of our network, SAJA. The right diagram shows the architecture of SAJA, and the left and middle shows the two building blocks. SAJA consists of Z-wise feed-forward network and a stack of self-attention blocks feed-forward again, and followed by Z-wise softmax. In the self-attention block, the multi-head means each block computes multiple self-attention in parallel. And all layers except self-attentions are Z-wise operation, and self-attention compute just a summation of Z's in the event. So SAJA is invariant on the Z permutation, and this property can be used to open the black box of SAJA with Monte Carlo simulation information. Now let's move to our experimental setup. We generate fully hadronic top pair production events with up to 2 additional Z at the next leading order using MATGraph and Pythia. And also we generate QCD merge-Z events at the leading order to check the performance on the background. And we perform a fast detector simulation using Delphis with CMS configuration card. And for Z clustering, we use an anti-KT algorithm with a parameter R of 0.4. For the selection, we follow the trigger selection using CMS TT all Z analysis. Z selection criteria are PT higher than 13 GB, eta less than 2.4. And at the event level, we require at least 6 Z, at least 1 BTAC Z of the 6 most energetic Zs. And 6 energetic PT is required to be higher than 40 GB. And finally, we require the HT, which is the scalar sum of all Z in the event, is required to be higher than 450 GB. After selection, we perform the Z pattern matching to give the truth label to the model. When all patterns are geometrically matched to Zs throughout the ambiguity, the event is said to be matched, and we use only the matched event to train the deep learning model, but we also test model with unmatched TT events. At the bottom, the left plot shows the Z multiplicity distribution after matching, and the right one shows the fractional matched TT events where all patterns can be matched with the most energetic NZs without considering BTAC information. Therefore, we can see that a large fraction of the correct assignment can only be achieved when most of the Z are used in the event. This is difficult to do in permutation-based assignment method. For the training, we use all Zs in the event, and for simplicity, the Z is represented as high-level reconstructed variable, transverse momentum, eta, phi, and pt divided by ht, btech. And furthermore, we investigate the jet shape information to test the So we follow the CMS paper. So we use a jet energy sharing variable, PTD, and major and minor axis of the jet axis in jet axis in the eta phi space, and charged hadron, neutral hadron, electron, muon, and photon multiplicities. Then we apply min-max scaling to all features except beta, which is the only true pairs from Delphis. Also, we studied the deep learning uncertainty to suppress poor jet pattern assignment. Note that this uncertainty is machine learning side terminology. Among various kinds of uncertainty, we use predictive entropy, which quantifies the uncertainty in the prediction of the classifier, where high entropy implies low confidence in the assignment and low entropy implies high confidence in prediction. So we measure the event by averaging entropy over all jet in the event. And we use this predictive entropy as a cut. You can see the normalized entropy distribution at the bottom plot. And also the uncertainty is also used to detect out of distribution test data, which is exactly correspond to QCD in this study. And you can see the QCD distribution has a peak near 0.5, is far from other distribution. As a baseline study, we perform kinematic likely fitting using the KFT library. And we tried two cases because of permutation problem. The first case is the most energetic 6 jet. In this case, there are 18 permutation on average. The second one is the up to 7 most energetic jets. In this case, there is 126 permutation on average. When the best permutation has a likelihood lower than the threshold, we do not select this event, and this detouring strategy is very general in other analysis. And let's move to the result. We measure the fraction of the correct assignment and also the rejection rate of unmatched TT and QCD multi-jet events. We visualize the performance as a Rokov style. 3 plots share the x-axis, which is the fraction of correct assignment. And from top to the bottom, the y-axis is 1 minus a fraction of wrong assignment, and middle is unmatched TT rejection rate, and bottom is QCD rejection rate. The more the curve is toward the top right, the better performance. And we can see that SAJA shows better performance compared to the KL-theta. Also, predictive entropy not only reduces a lot of QCD and unmatched TT without additional training process. And jet shape increased the fraction of correct assignment. And these two figures shows the reconstructed mass of W boson and top-quark. And for this plot, we use the SAJA network with jet shape and apply the entropy cut of 0.1. And one of the nice properties of attention-based model is that we can see what model has learned by visualizing the attention matrices. This figure shows the average of attention matrices for the correct assignment in the matched TT events. Since SAJA is invariant on the jet permutation, we can sort the jet using the jet pattern matching information for display purpose. B and B bar is just bottom quark and anti-bottom quark, and W1 plus indicate higher PT quark from decay products of W boson. In the first block, you can see the diagonal component has highest value in each row. Therefore, we can think that the first block is the stage of learning the representation of jet itself. And the middle three blocks show a relatively flat distribution and can be a stage to learn the representation of the events. In the last two blocks, there's no dependencies on the jet itself. In the last block, we can see the jets strongly attend to the jets from the same top-quark. So the last two blocks work as a staging to extract information needed for the jet pattern assignment. Also, we measure the inference time. This graph shows the average inference time per event. The x-axis is batch size only for SAJA. Note that solid KL-filter lines are constant because KL-filter doesn't support batch processing. The SAJA network outperforms KL-filter without batching and can achieve 2 orders of magnitude speed up in inference time with a large batch size. To summarize, we introduced the SAJA network for jet pattern assignment without requiring jet permutations. SAJA shows better jet pattern assignment and background rejection performance compared to KL-filter. Also, predictive entropy enable the performance improvement without additional training process. And finally, SAJA is fast even without GPU acceleration and can be extended to topologies with arbitrary number of jets and assignment categories. Thanks.
Okay, so wonderful. I mean, it's great. I mean, looks like it's not just better than kinematic likelihood theta. It's far better than the kinematic likelihood looks like. So thank you for your presentation. So are there any questions to Seungjin? We have still 5 minutes more. Yes, Elizabeth. You can turn on the mic.
Hello, thank you very much for this interesting presentation. My question is, so you applied your method, your network to all hadronic events. And of course, these are the most complicated events. And in fact, KL-filter was never optimized for those events. It was designed for lepton plus jets events initially. So my question is, do you have a feeling by how much you would improve with your method the reconstruction of lepton plus jets events, which are used in the majority of properties analysis?
I think I can hard to tell because we don't try it. So, but I think the improvement is not impressive in this than in this case.
So what you mean? I mean, so the question is, for this fully hadronic event, your machine learning, like SAJA, do much better than the kinematic likelihood, but including the leptonic channel, then it might be difficult to get such a nice improvement. This is what I heard from Elizabeth, right?
This is what I would suspect, but maybe I'm wrong. That's why I'm asking the author. Yeah,
I see. I think it's really worthwhile to try with some leptonic, including the leptonic channel, because this is only the study with the fully hadronic events. Yep.
No, I know that even relatively simple BDT can improve performance of KL-filter, but not as dramatically as here.
That's
why I was curious. Okay, thanks.
Yep, great. Thank you so much for the question. And Marcel?
Yeah, I was wondering if it works better, it must be using information that KLFitter isn't using. Is it clear which information it's picking up? And do you have a feeling of how robust that information is? Right, we rely on Monte Carlo probably to teach it what to do, and maybe at next to next leading order things will be different again. Can you comment on this?
I think that's a very good question. We'd like to try some alternate Monte Carlos for this, but we haven't looked into that yet. So far, we just have the network up and running.
Right, you could indeed test with some other Monte Carlo codes to see whether the performance is as good as it was with the training samples. But do you have an idea which exact information you're picking up that KLFitter is missing? Can you give me an idea?
Maybe I think the improvement comes from the use of all jet in the event.
Okay, so KLFitter stops after the first 4 or 5 jets.
Yes.
No, you can use more, of course, but then you also have more permutations, and that brings some mistakes as well, right?
Let's try it just. Can you see this? Can you see this figure? When we use 8 jet in the event, up to 8 jet, the average inference time is 80 seconds. So it is horrible.
Impossible to use.
Yeah.
Over a large data sample.
Okay, so right, you're able to use 2 additional jets, and KLFitter becomes impractical at that point.
Yeah.
Okay. But the speed is only one parameter in performance, right? We're not talking about speed here. What we're interested in is understanding where the information comes from. So for the maybe, I don't know what slide 15 means, but maybe there's a bit more knowledge there. What are these average attention matrices? Because I remember here we're talking about how well the B and the W's are matched to each other, is it? Again, and that was, sorry for interjecting like this, but I think it was also appropriate. That was my question. I wanted to understand the slide 15 a bit more. What does it mean? What is the definition of the attention matrix?
Okay. The attention, the exact computation of attentions are here. Firstly, we transform the jet reconstruction variable in this way. So we transform 3 times. The Q means query, and K means key, and V means value. And then we compute the matrix multiplication between Q and K. So the element of E indicate the response between them. And then we normalize its normalized rho using the softmax, and then we multiply attention matrices to value. So it indicates how these 2 jets are correlated, but it can be it's hard to interpret it in human language because deep learning is black box. But we can. But this matrices shows the model learn what model learn, but it is hard to tell about. It is hard to distill what model learn.
So for example, Seungjin, so if you look at this page, the block number 1, the most left upper part is BB. So BB is 0.32. And what it means 0.32 here?
It is just relative score.
So one means what then? One means
the B.
B is reconstructed as B 100%. That's one. And 0 means always fixed, something like that.
Yeah.
Okay. So then this is 32% of B is identified as as B, for example. Okay.
It means something like the value for B that is returned from this self-attention block comes 30% from B. So there's going to be some linear transform that gives you the output values, and each jet is going to have a value sort of summed over each of the output values of all the other jets in the event. And that means that 30% of the B jet output is coming from the B jet itself, 10% from, or 20%, sorry, from the W1, 14 from the W2. So it's sort of picking out how much of that output should be coming from the B itself. And these are all just very basic linear transformations of the inputs.
I see. Marcel?
Yes?
You raise your hand.
Oh, no, sorry. That was answered already. I should have.
Okay. So we actually running out of time, but we still have the general discussion time. So if you have any question to Seungjin and also for Soham, you can raise your hand. Any questions for Seungjin and Soham?
Yes, this is Francesco again. Actually,
Yes.
I wanted to go back to Sohan, and maybe we also go back to Seungjin. Sohan, you were mentioning that you were using 1.5 radius for your exercise. And I was wondering, have you tried 1.0 radius? How dependent is the performance on the radius? Have you checked that? Because I mean, we also use 1.0 radii for the measurement. And first of all, also thanks for the previous reply where you were saying that in fact you were not using truth information to check the performance, if I understood it correctly. I mean that you're using some proxies. I mean experimental proxies for photons and neutrons.
Francesco. Somehow,
yeah.
I think we lost Soham. Soham, are you there?
Okay.
He was
right.
here.
I didn't see him.
Yeah, he was here just 5 minutes ago. Then, oh, okay. So we lost him. So do you have any questions for Seungjin then?
Yes, I wanted to ask about the performance. I mean, I wanted to stress again one of the points that, in a sense, Marcel was making. All these performances that we're looking at, they're always compared to, I presume, the truth information, right? I.e., the Parton jet assignment done from truth. Is that correct? I mean, is the reference the truth jet assignment done from in a Partonic way, right?
Yes.
And so, how do you do this reference assignment? Because again, in reality, the performance is always a relative performance. The fact that the Parton is a really not well defined entity in Monte Carlo. It also has its own underlying ambiguity. So do you use a delta R match? What do you do? How do you define the Parton is that a jet is assigned to a Parton using truth information? That is the question. And how dependent is that on the parameters you choose?
I perform jet Parton matching to give truth label. And also I test unmatched case.
So basically, you are relying on the true jet, and then reconstruct jet, the angle between these two jet, and also the momentum or whatever. So
yeah, I just use geometric matching.
I see. So delta R is less than 0.3.
Yes.
All right.
Go to the top mass.
Yep.
So you tried varying the 0.3? Varying the 0.3? I mean, it's a typical thing. Sure, distances. I assuming you're not doing it in the boosted regime. This is in the bulk, isn't it? I mean, it's
We're just trying to use 0.3.
Yeah, I think this is a good question. I mean, whether you just use fixed 0.3 value, or you vary this value according to the A or whatever.
I didn't vary the jet matching criteria.
I mean, things can become unstable if you change 0.3. Well, depending on the algorithm, of course.
Maybe mostly depending on eta, because of the detector granularity is different from middle barrel to end cap.
Yeah, that also will have an impact. But I mean, TT bar jets are predominantly central. So one would expect that the partonic flow is in a region, hopefully in a well-controlled region. However, another robustness check is to change the matching scheme and look at how your performance changes. Because you have a moving reference. You see, it's not, the jet parton matching is also ambiguous by itself at a certain level. In well-separated event, it isn't.
I see. I think it's really worth to do. This is okay. Are you okay, Francisco? Then
yes, thanks.
All right, great. So we are exactly the time we promised is 25 now. So we have now 25 minutes more for the coffee break, and we will see you with the Thomas in the second session. Thank you so much for the speakers. Thank you for participating, everybody. See you later.
Thank you.
Yes, see you soon.
Thank you.
Yep.
Hello, does anyone wants to try and test sharing?
Yeah, I see Kacper and Adrian are connected.
Maybe they will try to share the screen. Kacper, Adrian?
Maybe they're in a coffee break.
Okay, next coffee break.
Yeah, we have tried all the speakers for this session. Then we just have to try the speakers for the next session in the next coffee break. I think that's a good plan.
Okay.
Thank you. Okay. Hello, everyone. It's almost 9:50. So let's start thinking about getting back to it. Welcome back to the fourth session of the Electroweak and Top Physics parallel session. My name is Soham Bhattacharya, and I will be your chair for this section of the session. Behind the username top-quark and Electroweak physics, there's a real person hiding. He's our Zoom technical assistant, and his name is Sasha. If you have any difficulties, please turn to him via chat. In particular, he should be ready to share your slides if you would rather not share them, or if you have any difficulties sharing them yourselves. At the moment, we have 24 participants connected. Great attendance. Thanks everyone for being here. We will now have 3 talks, each 18 plus 7 minutes. This will be followed by a 10-minute discussion session. After that, we'll break for coffee for 20 minutes. All the talks in this session pertain in one way or another to efforts of going beyond the standard model. The first two are within the framework of standard model effective field theories. And the last one is a little more traditional, assuming hypothetical particles with general couplings. So I remind everyone to mute your microphone when you do not speak. When you want to speak, please switch on your video and start by saying your name. If you do not have an option of using video, consider uploading a recent picture of yourself into your Zoom profile. We should have plenty of time for discussion, either right after the talk or in general discussion session at the end of the session. So I encourage you not to be shy. And if you want to ask a question, raise your hand if you know and are able to. Otherwise, just unmute yourself, unmute your microphone and speak up. Feel free to also use Zoom chat or our Mattermost channel to post questions if you can't speak. I would like to also add that at the end of not this section, but at the end of the session, so the following section, we will try to compete in the Zoom picture session, picture challenge. So I will ask you all to enable your video streams, and we'll take a screenshot. I hope you're all fine with that, and I think it can be good fun. I suggest we start with the talks. So first we'll have Martin, then Peter, and last Mohammed. Martin, are you there? Can you
yes, hello.
Speaking? Yeah, hello. We can hear you all right.
Should I share my screen, right?
Yes, please.
Okay. Can you see my slide?
Yes, we can see your slide.
Okay. So good morning, everybody. I'm Martín Perelló, working at ICHEP in Valencia, and I'm going to present my work on top electro-weak couplings, top-quark electro-weak couplings. I'll present current constraints, prospects, and the impact of a combined top-Higgs fit in an effective field theory approach. Of course, I have to thank a lot of people for different inputs and contributions. So first, a bit of motivation. We know that now the big last success of the standard model was the discovery of the Higgs boson in 2012. And now we still have to understand a lot of things like dark matter or the neutrino masses. We also have a lot of decides like great unification theory. And the problem is that at the moment we have very few hints. So we have decided to contribute or to study or to go beyond the standard model by studying the top-quark. And the reason is that we know that there are some models beyond the standard model that have strong couplings to the top-quark. Also, the top-quark at this point has never been produced in a lepton collider. So we think that in the future generation of colliders that in principle should be an electron-positron collider, we could do precision measurements in the top-quark sector. So this definitely would give us a bright window to new physics. So this is our motivation for studying the top-quark couplings. And some years ago, we used a form factor approach in which we had a process, for instance, TT bar X, and we added to the Lagrangian some new terms respecting the standard model symmetries that were expected to be zero on the standard model. And these form factors collected the strength of these new pieces. And we did physics on that. At some point, we decided to change, and we decided to change an effective field theory approach because we thought, we think it is a more fundamental representation. At the end, you have your effective field theory Lagrangian with the operators you use for construct your Lagrangian, and you calculate your observables, and maybe there are some operators that are shared in different observables. And at the end, with this approach, is very useful for benchmark studies, for instance. You have here an example of a global fit of effective operators on the top-quark in a total of 34 parameters. So before introducing the operators we have studied, let me motivate why we have decided to also include the bottom quark in our studies. The reason is that the top and the bottom quark are part of the same doublet in SU2. And this means that when you construct the coupling, the left coupling to the set, the effective operators that represent these couplings are shared. And you have here the formula. One is the operators I taken about phi q1 and phi q3. And one, in the case of the top, there is a minus. In the case of the bottom, there is a plus. And this means a very nice complementarity between top measurements and bottom measurements for constraining both at the same time. So we decided to not also include top quark operators, but also bottom quark operators. And this is our basis. We have a total of 10 operators. This is dimension 6 operators in the Lagrangian expansion. They are all electro-weak, 2 fermion operators. This means that at the moment we have excluded QCD operators, and we also have excluded in the first step the contact interactions. So these operators represent the left and right couplings, left and right-handed couplings of the top and bottom quark to the set boson. Also the charge current interaction, it's the WTB vertex. The electro-weak dipoles of the top and the bottom, and the top Yukawa. So for constraining this set of 10 operators, we have used data from the LHeC. Basically, all the data is from the run 2 at 13 TVs. We have production of associated processes to associated TT bar Higgs, TT bar C, W, and gamma. We also have the single top channels. We have also included information from the top decay, in particular the W LHeC fractions. In this case, the data is from the run 1 at 8 TVs. And as we are including bottom quark operators, we have also used data from LHeC and SLC. So in this plot in the bottom, what I want to show is the dependence. This represents the individual fit of each operator to the best observable, the observable that gives the best constraint and the second best. And what we find is that there is a very good interplay between the operators that we in our set and the observables that we have chosen. And this means basically that, for instance, we don't have a single observable that carries all the dependencies of the operators, or that maybe there is an operator that doesn't appear. At the end, there is a good representation of all the operators in the observables. And this is very nice because at the end, we have to have in mind that this is LHeC data, that it's hadron data, and we are trying to fit electro-weak top couplings. So this is the result of the fit, of the global fit. This is a Bayesian fit. We have used HEP fit, that's open source, and this represents 68% probability. The red bar represents the individual fit, yes, when only one operator runs. And the marginalized is the global fit itself when all the operators are running in the fit. So we find that the fit is robust. And again, this is good because it's electro-weak fit in the LHeC. All the coefficients are in agreement with the standard model. And we know that this is not all the global we can go, because at the end we have excluded QCD, we don't have contact interactions, but with this motivated set of 10 operators, we're very happy because we think that it's more robust than, for instance, if you simply interpret a specific measurement in terms of a single parameter. So we are happy with the results. Also, the bounds themselves are not that good. At the end, we have very wide bounds. And this motivates us of thinking in the future, in prospects. The first we have in the future is the high luminosity scenario for the LHeC. For that study, we have thought about two different scenarios, one more conservative and the other more optimistic. The conservative is S1, and we simply reduce the statistical uncertainty of the observables with the new luminosity we would achieve in the high lumi. And we have S2 that is more optimistic because we reduce statistical and systematic again with the new luminosity. But also we think that in that period of time between now and the collection of data, the theory will be reduced a factor 2 also. And here you have the results. The first column represents the previous results, but now I only represent uncertainty without the central value. And we have added two columns representing S1 and S2. The solid bar represents, again, the individual limit, and the full bar represents the marginalized fit. And again, we find that there is some improvement in some of the operators, but this improvement is not that impressive, because although we are collecting more luminosity at the end, it's still hadron data. So what we want to do really in electro-weak fit, and my motivation in the top-quark was that we need an electron-positron collider to achieve or to have precision measurements on the top-quark sector. And this is the physics we can do in an electron-positron collider. This is E plus E minus going to X. We have to have in mind that we start to produce top pairs at 350 GeV. So below there, we only can add dB bar measurements. And this is important because if we go to the different possibilities of future colliders, we have first the ILC in Japan, that the first point is the baseline energy is 250 GeVs with a possible upgrade to 500 GeVs. Also, there are other energies that were presented in the technical design report. It's a GigaSet program running on the set pole at 1 TeV. Also, the ILC allow for beam polarization, in both cases, in both beams, the electron and the positron. We also have CLIC, that it's based at CERN, working at 380 GeVs, 1.5 and 3 TeVs. Again, we can polarize the beams, but in the case of CLIC, we only polarize the electron beam. And finally, we have FCC that at CERN again, that it's planned to be an hadron circular collider, but working at 100 TeV, but with a possible first stage working on an electron positron first stage, like in LHeC and LHeC. In this work, we only have, in this presentation, I will only show the case of ILC. We have similar feeds using the CLIC program, but now I will only present the ILC case. The first point we find in the ILC is 250. As I said, at 250 we don't have tops, but we can include dB bar. In this case, we include the cross-section and the forward-backward asymmetry of the dB bar production with two polarizations that they are allowed by the ILC. You have a very interesting talk by Adrian Irles today about the reconstruction of dB bar at these energies. And what we find in the plot, we have added this extra green bar, is that, of course, the operators that represent pure bottom couplings are reduced in the global fit. And other interesting thing is that if you look at the second and third columns, FIQ3 and FIQ1, that remember that are the left couplings shared in top, bottom, and top, you see that in the global fit, these bounds are not reduced that high, but in the individual fit, they are reduced a lot because, of course, as they are shared in the bottom operators, and we're adding bottom measurements, this individual fit is very, very good for them. The first point of the ILC in which we have tops is ILC working at 500 GeVs. And here again, we include BB bar cross-section and forward-backward asymmetry for BB bar. And in the case of the TT bar, we include the motivated optimal observables that are motivated for this concrete set of operators, and in principle means that these optimal observables would give you the best constraints in this particular fit using the kinematics information from the top decay. And now we have added this light green bar, and finally we find that the top operators are reduced now. The bounds are very good, 1 or 2 orders of magnitude better than the bounds we had at the LHeC. There are 2 exceptions. The first one is T5, that is the 6th column. The reason is that we at this point have only added TT bar, but not TT bar Higgs, and this has been done separately, and I will discuss it now. And the other is the last column, that is phi TB, that represents the WTB vertex. And again, the reason is that we don't have at this point any single top or top decay, but it's something that we can do, and we know that if we do this, we will reduce this uncertainty too. So as I was mentioning, we have studied the top Yukawa separately. Also, this is also the top Yukawa is included in the global fit. You have here in this table in the last 2 rows, the circle is, this is the uncertainty of the top Yukawa itself, not the operator, but the transformation to the top Yukawa. And you see the evolution from the current data from LHeC run 2 plus LEP and SLC to the prospects. And we see that with ILC 500 CVs that we have top, now we have added TT bar Higgs. We have an uncertainty of 6.4. The best point at ILC is not 500, but 550. We reduced the uncertainty almost to the half. But the best one would be a complete run of the ILC, including 1 TV. Also, CLIR has reported the uncertainty in the top Yukawa for a single energy that would give the best result with a single energy. So this is
you have about 2 minutes left. Thank you.
Okay, I'm finishing. So this is a direct constraint of the top Yukawa, but Mitov and et al. Motivated to extract the top Yukawa from indirect constraints, but using Higgs to gluon and gamma, because in the individual fit they show that there were a very good response of the top Yukawa, achieving very low uncertainties, as you have in the circle. So this motivated us to do, okay, we have this Higgs decay with the top entering in the loops, so why not do a combined fit in between top and Higgs? So this was based in a previous Higgs coupling fit of these 2 papers that they had a total of 22 operators for the Higgs boson, and we have added 7 more in the case of the top that are entering in the loops. And I show here the results of a concrete scenario in, again, ILC at 250. The first in the plot on the top, for instance, the first column represents the Higgs fit without tops. If we add the tops in the loops, adding the current constraints, we see that these bounds are degraded, but we nearly recover the original values if we add the S2 scenario that I remember that was the most optimistic case for the high luminosity. So at the end, we think that even if we do a combined Higgs top fit, we think that we can recover the original bounds of the Higgs in a grade of the top couplings bounds. So this brings me to my summary and conclusion. We have seen that a combined fit on the top and bottom quark is demonstrated to be robust using current data from LHeC run 2 and LEP. We improve an order, 1 or 2 order of magnitude, the existing data, the existing bounds, if we use electron positron data with producing tops, of course. And we have seen that we can do a combined Higgs top fit entering the tops in the Higgs loops if we include prospects for the tops that will mitigate the impact of the top operators in the Higgs sector. And that's all. Thank you.
Thank you, Martin, for your talk. Are there any questions?
Hello, Martin. This is Francesco speaking. Do you hear me?
Yeah, I can hear you.
Ciao. So I was wondering, it's more of a curiosity, on your slide 13, how come you change only 50 GeV and your uncertainty drops by a factor 2? I mean, the thing that you pointed out with the ILC 550.
Yeah, I think this point was motivated for this in particular. I cannot remember exactly why we decided 550 GeVs. It was not our idea, at least it wasn't my idea. I think it is something that it was known, maybe because now at that point there is an improvement in the cross section enough for this change. Yeah, I think
right,
so.
Martin. You're right on the threshold at 500. In fact, the 500 was chosen before the mass of the Higgs was known, of course, and before anyone had studied this. It turns out the 50 GeV give you a big enhancement in the cross section, in fact, the 3, I believe. And then the uncertainty is reduced by a factor 2.
Okay, so you're moving along. You're just riding the derivative if you want. And so you see the effect as soon as you move. Right,
it's just threshold. So there's large bound state effects like they are at TT bar thresholds. You get TT bar Higgs, a large enhancement of the cross section. And at 550, you're sufficiently on that peak that the cross section enhances by a large factor. And in the end, it's just statistical dominated uncertainty. So you fully gain from that.
Thanks.
Any more questions? I just have a quick question myself then. Can you go back to your bar charts plots? I don't remember which slide. It was the first one with an improvement, I think maybe ILC.
This one? Or the columns one?
No, the columns one. Yes.
Okay.
You said something about not showing the central value, only the uncertainty?
Yeah, in this, yes. In this case, yeah.
Can you explain this a little bit more, because it was a little bit too fast for me?
Yes, from in this case, in the case of the bars plot, the fit is centered in the we do the measurement minus the predicted as usual, and so the central value falls wherever, and it's this plot. In this case, simply for comparing with the prospects, as we don't have a central value for prospects, of course, we only have an estimate of the sensitivity. We center the fit to the standard model. So the fit only gives us a prospect of the uncertainty of the scale we can achieve, but not about the central value.
Right. And the hatched bits, what is that exactly?
Sorry, what? Can you repeat?
The hatched bits, not the solid ones, not the filled ones, but the hatched ones.
It's the marginalized fit again. Individual is solid, and the global fit is the full bar.
Okay, thank you. I see we have a raised hand from Peter.
Hi. So, how many sigmas is this? Is this 68%?
Yes, this is 68% probability. Yeah.
Okay. Thank you.
Mm-hmm.
If there are no more questions, I suggest we move to the next talk. Thank you again, Martin, for a nice talk.
Thank you
for your answers to your questions. Peter, can you try to share your slides and your audio?
Yeah, so okay, can you see the slides?
Yeah, we can see your slides and we can hear you.
Good.
Just go ahead at your convenience.
Okay, yeah, so I'm Peter. Hi everyone. I'm talking about new results from TopFitter. So let's answer the most obvious question: what is TopFitter? TopFitter is a tool for global fits of Wilson coefficients in the top-quark sector of the standard model effective field theory to experimental data. And earlier publications, TD bar production and single top production mainly was fitted separately. So 12 operators could be constrained, where up to 6 operators were fitted simultaneously. And that fit used about 226 degrees of freedom from data sets from Tevatron and the LHeC, mostly run 1. So a couple of years after that, work on an improved version of TopFitter started. And the first application was to constrain electro-weak couplings in composite Higgs model. But in the last years, top global fits somehow became quite popular, and many groups started to do these fits. For example, SMAFIT collaboration or W et al. and SFitter. We just heard a talk actually about that. So that seems to be quite popular, and TopFitter of course wants to also put forward an updated version of the old fit, where we like to put some emphasis on aspects that are not that well studied or even neglected. So first of all, we would like to include a comprehensive data set from Tevatron LHeC run 1 and run 2, extending the sets of included operators, and in particular also study the impact of double operator insertions on the fit, and include observables at the level of decayed top quarks. And finally, but I won't be talking about that today, but we also want to include fiducial measurements in the fit. So what is the standard model effective field theory? I probably don't have to say much about this. Could say much about it, but just think of it as an expansion of the Lagrangian in terms of 1 over lambda, where lambda is a new physics scale, and each term has operators of mass dimension larger than 4, and they come with coefficients. They're called Wilson coefficients, and they basically parameterize the strength of this effective coupling. So this math basically parameterizes high-scale new physics in terms of Wilson coefficients. And this is a very general approach to new physics and allows us to constrain a large class of high-scale BSM models. So if you look at the expansion a little bit more close, then we see that first term is actually not so relevant for us. It's more relevant for neutrino physics. So we start with the 1 over lambda squared term, which is that of dimension 6 operators. And there are 59 of them in this math, and if you would count all the fermion combinations, then all the flavor combinations, then you would end up with nearly 2,500 operators. So usually we impose some kind of flavor symmetry to reduce this to a manageable size. So the next to leading EFT order of lepton number conserving operators is dimension 8. And at that order, we have already nearly 900 operators, not counting flavor. So that is quite a lot and really difficult to handle for global fits. So usually this is neglected. There are exceptions, but usually this is neglected. And so we will also neglect that here. If we go away from the Lagrangian and look at the matrix element level, we see the structure of the contributions. So there's a linear part, or the part that is linear in the Wilson coefficients, which goes as 1 over lambda squared, and this is the only contribution to this order. And then we have contributions from dimension 6 operators to the next order, 1 over lambda to the 4th, where we have double operator insertion interfering with the standard model, and two single operator insertions interfering with each other. And finally, there's a third component or contribution to the order 1 over lambda to the 4, which comes from dimension 8 operators. But as I said, we neglect them. So this structure also translates into a nice multivariate polynomial form in the cross section. So this makes it quite easy and fast to sample the parameter space of Wilson coefficients. However, if you include top decay, this simple structure is broken, and one has to deal with that. So going away from the more general discussion towards the actual top sector of this math, so we define the top sector as all the operators that include at least one top quark, and they can be divided into two parts: 2 fermion operators and 4 fermion operators. And the 2 fermion operators again can be divided into 3 groups according to the number of Higgs doublets. So those with 1 Higgs doublet are the dipole operators. Then there are the neutral and charged current operators with 2 Higgs doublets, and the Yukawa-like operators with 3 Higgs doublets. There can be also CP violation among some of these operators, and we impose the flavor symmetry written down here to restrict the number of operators to the number you see here. So the 4 fermion part is a little bit more involved. It looks like a very busy slide, but it's just to illustrate what kind of operators contribute there. Basically, the important thing is that you can have 3 categories: 4 fermion operators coupling heavy and light quarks, those coupling only heavy quarks, and those coupling quarks with leptons. And again, the flavor assumption really reduces the allowed number of operators. So in terms of numbers, there are 42 top operators. This is counting all the flavor combinations according to this assumption. And if you allow for CP violation, then this rises to 52 operators. In TopFitter, we fit a subset of 30 operators, and we only we don't allow for CP violation for the moment. And in addition, we also fit a non-top operator, which is related to the 3-gluon vertex. So we have discussed the operators, but this is quite abstract. So I think the most important and phenomenologically relevant part is how can we probe these operators? How can we constrain them? And this picture here shows one of the some of the most fitted processes in top physics, and also measured ones actually, and the corresponding operators. And you see there's a lot of crosstalk between processes and operators, and so it's very important to include as many operators and processes as possible to be as model agnostic as possible. This is just a motivational slide for being as global as possible in the fit. We have seen in the previous slide that one kind of operator is missing, namely the top lepton operators. And this is because what I showed on that slide was just at the level of top-quark production. So if we include decay or associated production with decay of the Z boson into 2 leptons, for example, then we have access to top lepton coupling operators, and there are already existing constraints, as you can see on the slides, and they come from leptonic B decays and from dilepton production at the LHeC. But these constraints are rather indirect, so it would be interesting to see what can a dedicated top fit say about these operators. Also, another motivation for taking the decay into account is that we can actually, as you can see in the slide, in the decay we are also sensitive to operators that already occur in the production. So this gives us just additional constraining power. Then, of course, the the decay is sensitive to new kind of operators of the lepton quark coupling type, and also what I don't have time to discuss much, but decay observable at the level of decay products, they also give us more sensitivity to decay and also to production. Yeah. So in the decay, just shortly, this nice multivariate polynomial structure is lost a little bit because of the top width, which comes into play, which also depends on the Wilson coefficients. So in order to handle that, one has to just calculate these two, the numerator and denominator separately, and then combine them. And this, so one can still do the parameter scan very quickly, and then just combine these two quantities to get the narrow width approximation, though, for decay cross section. So how does TopFitter work? We start with a UFO model implementation of the SMEFT called SMEFT-Sim. This is fed into MATGraph. And at the same time, we have, as another input, what we call analysis description file, which has all the information about the analysis, like what kind of process, what observables, but also what cuts, and of course the experimental data as well. So at different stages of the workflow, this file gives the relevant information. So here it would be, for example, what kind of process to generate with MATGraph, and what kind of cuts to set. MATGraph generates standard model next to leading order samples with scale and PDF variation. So, and the same for the EFT contribution, but only at leading order. And also with variation, but in particular for each EFT contribution means linear part and cross terms and squared part and so on. All that is generated separately. And this is fed through our analysis framework, which occasionally also applies some NLO K factors to the standard model where appropriate and available. And the analysis then just calculates, with the help of the information from the analysis description file, all the observables and does the correct binning and so on. So we end up with basically two-dimensional array of observables and variations, and then for each contribution of the EFT as well. And this is...
Excuse me, you have about 5 minutes left. Thank you.
That's good, thanks. So we store this into an HDF5 file, and that is the generation part finished. Then the fitting part would take this information from the HDF5 and combine different contributions from the standard model and the EFT according to the point in Wilson coefficient space that is needed for the fit at any given time. And then from this combination, we again get the observable predictions for all kind of variations at a given parameter point. And from that, we can calculate the central value of each observable and an associated theoretical error. And this is then fed into the chi-square together with the experimental values, of course. So the experimental input to the fit is, first I show you the target input. This is what we would like, what we are aiming for. So that is data from Tevatron and LHeC, 78 analysis with over 600 degrees of freedom in 11 processes, and including the top decay. However, today I can only show you a preliminary subset of that, which still includes 45 analysis and 179 degrees of freedom in 9 processes, and also including the top decay. So the result looks like that. Yeah, on the left, the very left, you have this 3 gluon operator, and then the 2 fermion operators, then 4 fermion operators, 4 quark operators, and the last 4 are the lepton quark operators. So first of all, these are 95% confidence level limits, We can constrain individually 27 operators from the 31 that we took out to constrain actually, but 4 are not constrained by the data in that preliminary fit. And 20 of the operators we can also find marginalized bounds. We include all dimensions 6 contributions up to order 1 over lambda to the 4th. And as you can see, all the heavy light 4-quark operators are constrained within 1, and we can even find individual top lepton operator constraints between 1 and 2. Then, just as a comparison, we can have a look what happens if we do not include this higher order EFT contribution. So on the top you see only the linear fit, and at the bottom you see the original fit, but without lepton operators here. So we see that some operators are missing because they just do not contribute at the linear level. So this is, of course, one cannot change this even at NLO. At NLO they contribute, but you still do not get bounds for them, at least not with the current data. Yeah, and actually one also would suspect that the inclusion of a full data set would reduce also the impact of the difference between using only the leading order or using the next to leading order in EFT approximation, because some of these operators you see here, or Wilson coefficients, they are quite impacted by the higher order, which we actually don't want, because this is only calculated to half, so to say. In conclusion, so let's recap the goals that we have. So we want to include a comprehensive data set. Well, we are on the way to that. The preliminary data set already shows promising results. We could extend the number of operators with respect to the previous TopFitter result, and also include lepton top operators, which have not been studied so far by global top fits. The study of double operator insertions is underway. In the results that they show, all the double insertions are included, at least for the results that have the 1 over lambda to the 4th contribution in them, and we just have to compare them with a single insertion only result, which is still in the making. We also include observables at the decay top-quark level, and we will include more, of course, in the target set. Inclusion of fiducial measurements is also work in progress, but wasn't really mentioned in this talk, but just want to flag this up. Okay, thank you for your attention.
Thank you very much, Peter, for your talk, and thank you for leaving plenty of time for the discussion. So let's ask the audience, are there any questions? Yes, we have a raised hand from Marcel.
Yeah, Peter, this looks very impressive. How do you treat correlations between all the measurements that you're including?
Yeah, that's a standard question. I didn't say much about that. Yeah, so we include all the correlations that we can get from the experiment, but you probably know that also that this is not always provided. So in that case, we do not assume any correlation. But I must say, this is just a preliminary result, but for the more detailed study, we will probably assume different kind of correlation models, like everything correlated, random correlation, no correlation,
right,
including given correlation, and then see what is the impact on the fit, to assess a little bit in the kind of uncertainty that is in the unknowns of the correlations.
Right. I guess the experiments have a lot of work to do to provide everything that you need, and And some of these measurements are quite old already, so it's doubtful that you'll ever get it.
Yeah, probably not. Yeah.
Right. So what we did in Martin's talk is, if there is an atlas and a CMS measurement, but they're not combined yet, we just picked the best one. That is a more conservative approach. You could assume some degree of correlation that is ad hoc and see how robust the fit is against that assumption.
Yeah, that is true. I mean, I said earlier there is this target set with over 600 degrees of freedom, but I think many of them will be correlated to some extent. So one probably has to reduce that number by picking out, for example, from one measurement only one distribution or so, to be on a safe side. At least one can provide an alternative result and see what is the impact. That is definitely a good way to do.
Right, and I guess we should encourage the LHeC top working group to perform combinations so that we do have the absolute or the exact input information for the legacy results.
Yeah.
Okay, thank you.
More questions?
Yeah, Daniel here, I have a question. Can you hear me?
Yeah, okay.
Yes, so basically, since these top measurements are very difficult and basically they all derive from a different final state from WWBB or even more complicated things, and then they're basically just corrected to the top cross-section level. Are you sure that basically these corrections that the experiments do still include these effects that you're looking for? Maybe are they corrected out artificially in the measurement procedure?
We cannot be 100% sure, of course, but that's actually a motivation to go to fiducial measurements, where there is less model assumption due to the unfolding on two-parton level. At the moment, this is all parton level, so there is this extra degree of unfolding involved, and of course, this is always done with standard model Monte Carlo. And there are examples from, for example, Higgs measurements, where the experiment do a good job, and they include EFT corrections, and they measure, for example, dependence of the acceptance on the value of the Wilson coefficients, and they are quite strong dependencies. So I guess things like this will also happen in top physics or top processes. So it would be better if the experiment already would include these kind of corrections and give basically their likelihood for that. I mean, that would be the ideal case, and then fitting collaborations can use these likelihoods. But for the moment, we are stuck with the experimental data that we have here, and yeah.
I mean, you're looking for many subtle details, and of course, when doing such a measurement, many things can go wrong. It's basically being corrected out of the data finally. So once maybe you have set up all your fits, and one can go set by set through the measurements and see what can be improved. I mean, this can also then go just to the LHeC top working group as a recommendation how they should improve these measurements.
Yeah, definitely. This is actually also something where I see the future of these fits. I mean, the results that we present, they're all good and nice, but they have these problems that you say. And there's one thing, and the other thing is, if you look at concrete realizations of BSM physics at high scale, then this will actually induce correlations between the operators. And if you take this into account, you will get much tighter bounds, actually. So these marginalized things, they are really very conservative. But so actually the real future, I think, of this fits would be just to provide actually likelihoods to people that want to study BSM models, and then they can do the matching and do and find exclusions with help of the likelihood. And the other thing is what you said, provide input for the experiments to see which analyses are most sensitive, maybe even construct new observables, do the fits with new improved observables. or new processes that haven't been studied before, and then give directions for experimentalists. I think this is something interesting.
Yeah, thank you.
All right. Thank you, Peter, for your nice talk again, and thanks to everyone for a nice discussion. Remember, if there was a question you wanted to ask but didn't get a chance now, we have 10 minutes reserved for general discussion at the end of the section. So just write it down and wait for after the next talk. Mohammed, are you ready?
Hello, yes, can you hear me?
Yes, we can hear you.
Okay, and can you see my screen?
Yes, we can see your screen.
Okay, and my video?
Yes.
Okay, great. So, okay, so hi everyone. Can you see your face, Thomas, on the shared screen? Should I get rid of that?
No, don't worry.
Okay.
Just go ahead. Thanks.
So hi everyone. So I'm Mohammad Mahdi AlTakach, and I would like first to thank the organizers for giving me the opportunity to present this work here in the ICHEP 2020. This work was done in collaboration with Thomas Schiejo, Michael Klassen, Jean-Nicolas Lang, and Ingo Scheinbein for the calculation. And there's also an upcoming phenomenological study with John Butterworth through the MCNet program. So today I will present the NLO QCD correction to the electro-weak top-pair production beyond the standard model. And by beyond the standard model, I mean that we include new heavy resonances. And these resonances can be produced by models with extra U1 or SU2 symmetries. So if one wants an extra Z prime, IU1 is enough, but to obtain an additional W prime and SU2 is mandatory. So even though the strongest constraints on the resonance comes from the leptonic final states, the top quark observables are still very interesting. Since the third generation plays a prominent role in the standard model, and it's quite conceivable that new physics couples predominantly to the top quark. Well, even for models that couples to leptons, top quark observables could play an important role to distinguish between different BSM scenarios. So this being said, so in 2015, Thomas Schiejo performed a calculation of NLO QCD correction to electro-weak top-pair production at the LHeC in the presence of a new heavy resonances, namely the Z prime boson. And this Z prime boson had generation non-universal but flavor diagonal couplings as to the standard model fermions, as one can see here in the illustrated picture. And this calculation also took into account the standard model and new physics interference, so between gamma Z and Z prime. And the result was implemented in the Powig box framework, where they edited the code in order to so that the initial state QED singularities can consistently treated. So a few words about the calculation. Here we show the partonic top quark pair production cross-section at the next to leading order. On the right-hand side of the equation, the indices, so the first index represent the power in alpha strong, and the second one, the power in alpha electroweak. So the first element is the standard model QCD. The third one is the NLO QCD correction to it. The fourth one is the electroweak correction to the standard model QCD. And the second and fifth are respectively the electroweak top quark pair production and the NLO QCD correction. And this is our calculation, the calculation that they've done. The last term is the electroweak correction to the electroweak top quark pair production, but we don't include this in the calculation. Okay, now let's show some sub-processes. So for the Born, we have the S-channel QQ bar initiated process. And we also, for virtual, have the same with an emitted and reabsorbed gluon in the initial and the final state. And the resonance here can be, as we said, either gamma or Z prime. Same for the real. So here we have quark initial state and also gluon quark. And again, the resonance can be gamma, Z, or Z prime. Well, now for the gluon quark channel, we have an initial state collinear divergence associated to the photon propagator. And this means that for the mass factorization procedure, one needs to introduce a photon PDF. And not only that, also one also has to include the photon-induced sub-process in the calculation. And it turns out that this channel is numerically important. So in summary, this was the first calculation of NLO correct to electro-weak top-pair production in the standard model. It was matched to parton shower at NLO plus PS accuracy within the public box framework, and the code was named PBZP. But however, this calculation lacks from some features. For example, it does not include the contribution of T-channel W and W prime. It also doesn't allow for Z prime with flavor non-diagonal couplings to the standard model fermions. And this motivates us to do this electro-weak top-pair production in the presence of heavy Z prime and W prime bosons at NLO QCD in LHeC, and this will be published soon. So again, now actually we reperformed the calculation completely, and this time using the Ricola 2 package, which is a public code that can calculate electro-weak and also QCD amplitudes for BSM physics at NLO accuracy once the BSM models are provided. Okay, so again, the amplitudes were implemented in the Monte Carlo event generators within the power box framework. And this was the first use of Ricola 2 BSM amplitudes and NLO plus PS matched calculation. The code now include the T-channel W and W prime contribution. Also, it allows for general couplings for Z prime, so general, so generation non-universal and flavor non-diagonal couplings, as illustrated here in this picture, but not only for Z prime, but also for W prime. Again, the standard model interference effect is taken into account, including this time the W and W prime contributions. And this calculation was validated against the old one, and we found a full agreement. Again, we'll show some sub processes. As I mentioned, this is 5 flavor scheme, so we don't include top in the PDF, neither the weak bosons, but we do include the photon. So for the Born processes, we have an S channel, but this time flavor non-diagonal one, and also a T channel, flavor non-diagonal one. And so for the S channel, it's the resonance can be gamma, Z, or Z prime. And for the V, so in the T channel, it's W, W prime, Z prime. Same for the virtual, we have now a T channel. Also, we allow for flavor non-diagonal. And for the S channels, it's gamma, Z, Z prime, and W, W prime, Z prime for the T channel. Again, for the real quark, real contributions, now this first line is as the first calculation, but with flavor non-diagonal, and it allows also for gamma, Z, Z prime. This is quark initiated state, so diagrams. We have now also this contribution, the new one too, also flavor non-diagonal, and this time the V can be W, W prime, sorry, or Z prime. Same for the gluon quark initiated states, Z, gamma, Z prime for the first line, and the second T channel line. So we have W, W prime, Z prime included. So now to investigate the potential impact of this new feature in our new calculation, we'll first have to introduce some models. The first model we use is a sequential standard model, which is a toy model that includes heavy copies from Z and W of the standard model. The width is proportional to the mass of the resonances, and this model is widely used in the CMS and Atlas searches. I show here some the most strangest limits coming from the first, the leptonic final state. So we have a lower limit of 5.15 TeV for a ratio of width over mass equal to 3%. And for the same ratio in the hadronic observables, we have a lower limit of 2.7 TeV. And finally, the input parameters of this model are just the mass of the resonance. The second model we use is the leptophobic top color model. So this model is a model with an additional, an extra SU3 symmetry that only couples to the third generation. And the first SU3 symmetry those coupled to only first and second generation, the symmetry breaking is done by breaking the SU3-1 cross SU3-2 down to the SU3 color of the standard model. And also we have an additional U1 symmetry that is associated with a Z prime, and this to block the formation of bottom quark condensate. And again, now the U11 cross U12 symmetry is breaking down to the U1 hypercharge in the standard model. So in this model example of the top color, our Z prime only couples to the first and the third generation. And this again is a model that is frequently used in Atlas and CMS searches. So also most stringent limits here coming only from hadronic final state, since this is a leptophobic model. So we have a lower limit of 6.65 TeV for a ratio of 30%, and it decreases for 5.25 and 3.8 when the ratio decreases to 10 and 1% respectively. The input parameters in this model are, again, the mass of the resonance and also the ratio of the 2 U1 coupling constant. And finally, the last model we use this model to illustrate the generation non-universal and favor non-diagonal feature of our calculation. And this is the third family hypercharge model example case, where we have an extra U1 symmetry. And this model was invented to try to explain the neutral current B anomaly. And also it explains the heaviness of the third family fermions. For the most stringent limits here, we have a lower limit of 1.2 TeV. And finally, the input parameters of this model are, again, the mass of the resonance, the gauge coupling of the U1 symmetry, the additional one, and also the mixing angle between the third and second generation theta SB. So now let's show some numerical results. But first, I will have a few words about the setup and the inputs. So, of course, we generated our events using the new tools, the new PBZP and the LHeC format, where we had a stable on-shell top quark. We imposed, before generating the events, we imposed a generation cut on the invariant mass of the top pair of 0.75 mass of Z prime. And so by generation cut, we mean that this cut was imposed at the Born phase space level. And this is in order to obtain more events and the wanted regions. We used the Pythia to decay the stable top and elliptically, and also to shower the events. And on the fly, we used Revit to impose these fiducial cuts. So namely, a 0.5 radius of the beat jets, and we use the anti-KT algorithm for the jet definition, a transverse momentum greater than 25 GeV, and an absolute rapidity smaller than 2.5 TeV. Also, we show the results for different center of mass energy. So we will show something for 14 TeV and also for 27, 50, and 100 TeVs. We show a mass range of Z prime between 2 and 7.75 TeV. The mass of the top in this calculation was set to 173.2 GeV, and our PDF choice was the LUX QED, and PDF at NLO. And we set the renormalization and factorization scales to the square root of S hat. So now let's go to the results. So here we show results for integrated cross-section. So this is the electro-weak top pair production cross-section at next to leading order for 14 TeV center of mass energy for the electro-weak standard model, the sequential standard model, and TC and third family hypercharge versus the mass of Z prime. So as we see on the left side of the y-axis, this is the PP to Z prime plus Z plus W plus gamma interference included, where the blue line is the TC model, the red one is the sequential standard model, and the green one is the third family hypercharge model. The dashed black is the standard model. Everything is at NLO, as we said. And we can see here that actually the invariant mass cut that we imposed effectively suppressed the standard model cross-section for the sequential standard model and the TC model, but not for the third family hypercharge model. And this is because the third family hypercharge model cross-section is too small, actually. Also, we show the K factor, so the ratio of NLO over leading order cross sections for only sequential standard model in red and TC in blue, top color. So, and one can see that from 2 TeV to it started with 20% for the TC model and 24% in red for the sequential standard model, and it increases up to 30% at 5 TeV for the TC model and 36% for the sequential standard model. Also we show the same, but now versus the center of mass energy. So for 14, 27, 50, and 100 TeV, again, same Z prime, Z, W, and gamma interference included, same color code. Just to give an example about the expected events in this plot. So if we look to the high luminosity LHeC, so a center of mass energy of 14 TeV and a luminosity of 3 inverse autobahn, we see that we expect 130 kilo events for TC model, 18 kilo events for sequential standard model, and only 1.6 kilo events for third family hypercharged model. While for the high energy LHeC, so square root S equal 27 TeV and a luminosity of 15 inverse autobahn, we have 5.5 million events for TC. We have almost 900 kilo events for sequential standard model and 100 kilo events for third family hypercharged model design.
You have about 3 minutes left.
Okay, thank you. So also we show the K factor ratio. So here also for sequential standard model in red, TC in blue, and we see that with increasing energy, the K factor is decreasing. Okay, let's move on. So last but not least, we show the importance of the W contributions. So here we only, so again, it's electro-weak top pair production at NLO square root S equal 14 TeV, but only for sequential standard model. And here we compare with and without W contribution. So in blue, we have Z prime plus Z plus gamma interference included, while in red, it's Z prime plus Z plus gamma plus W interference also included. And below, we show the ratio of the two, where the precision is about 1%. And we see that it ranges between 2% to 12%. And this, just to give you an idea, this is after imposing all the cuts we spoke about. So to illustrate this, if we want to show the difference between W and without W, if no cuts were imposed, then the difference is 60%. And this difference decreases to 42% if only generation cut is included. And where we impose the fiducial cuts on top of the generation cuts, this is reduced to only 7%. So to summarize, we presented a complete new calculation here. So where we used the Recula package and we added W prime, where now the Z prime and W prime couplings are general. The T channel W contribution is included. Also, the standard model are again, so the standard model and new physical interference effects are again taken into account now with W and W prime. Again, the calculation was matched to parton shower at NLO plus PS accuracy within the Powick box framework. Also, we showed some numerical result to illustrate our features. So for sequential standard model, TC model, and third family hypercharged model example case. And hopefully a paper will be soon out about this. So thank you very much.
Thank you, Mohammed, for this really nice talk. Are there any questions? Yes, I see a raised hand from Yiji.
Yeah, hi, this is Yiji Kvita. So maybe I missed it, but I just would like to know maybe some details on the choice of the coupling of Z prime to fermions and whether there's a difference in the coupling to quarks and top quarks. It might be model dependent, but I'm just not familiar, but would like to know a little bit what you had to do for this.
Yeah. So here, as I said, so now we use Recula to calculate the amplitudes. So so now everything is included in the code, but one has to provide. So you have the option to provide whatever coupling you want to whatever quark, even if it's not physical even. So we have a general matrix. Okay. So if I understood your question well, so it depends really on the model. So for example, like for models like the third family hypercharged model, it allows for flavor and non-diagonal couplings. So I don't know if you see my cursor.
Yes.
So then in this case, you will have, so So first, in the previous calculation, we do allow for different couplings between generations. But now on top of that, also for flavor non-diagonal, so for the non-diagonal terms here, they can also be different. So the user has just to give this as an input, and then Ricola will calculate the amplitudes. It will be in PowerWig, and you will have the results. This answer
I see, that's nice. So what values did you choose for your numerical calculation?
So, for example, for the sequential standard model, these were the same as in the standard model, but the mass of the resonance is different. So also for the elliptophobic top color model, it's also generation non-universal, but flavor diagonal. But for the third family hypercharged model, I don't have the couplings, and so I don't memorize them. But we had flavor non-diagonal couplings, so we had term in non-diagonal terms for the couplings. Sorry, but I don't memorize the numbers, but I can send it to you if you want at some point.
No problem. Thank you.
You're welcome.
Thank you, Yuji. Any more questions? Christine?
Oops, sorry, unmute. I was wondering whether there is any measurements really targeting this at the experiments at the moment, or whether it's even possible to target this specifically.
Well, actually, now we are working with John on some phenomenological related to this calculation with Atlas analysis to compare this and find some exclusion limits. So, and this also can be used, for example, to provide the K factors for the experimentalists. I don't know if this answers the question.
I can perhaps add to this. So there are dedicated searches for heavy resonances in top pair final state, and this top color model is routinely searched for by Atlas and CMS, and basically what needs to be calculated are cross sections of electro-weak top pair production, including so at the moment only the Z prime contribution is included, no interference between standard model and the background.
Okay, I understand. Thank you.
Thanks so much.
All right, we are slowly in time for general discussion session. So if anyone has questions either to Mohammed or to any of the previous talks, now would be a great time to raise your hand or just to speak up.
Hello, this is Francesco speaking. Do you hear me?
Yes, go ahead.
Thanks, Thomas. So it's a question to Peter for the previous talk. First of all, I'd like to thank him a lot for the initial introduction. The didactic approach is extremely helpful, particularly in making sense of separating, classifying all the different operators. That is, I've seen many presentations, and this was probably one of the clearest ones in this respect, most useful for me. So thanks a lot. The question is related to one of the points that we, really, that's very much appreciated. The question is in relation to the discussion you had with Marcel before, the discussion about the inclusion of EFT corrections, of EFT information for the acceptances in the unfolding, or similar, if one does a profile likelihood fit for the generation of the likelihood. So are you willing to go a bit more specific on this? Because as you yourself have mentioned, one has options, right, in choosing the dependence on the EFT. How many parameters do I choose? How many items do I put in? So is it sufficient if one experiment simply provides these acceptance corrections as a function of a given parameter, and they are manifestly expressed. I mean, is it easy to replace them? Because one thinks, okay, these are acceptance corrections and so on. But in reality, in principle, you can redo the full unfolding or re-simulate the full response of your detector, assuming the EFT Lagrangian, right? You can say, I generate events with the EFT Lagrangian instead of generating them with the standard model, and I pass them through the full simulation. And then at that point, I have the full response matrix with starting off with the EFT Lagrangian, not only the acceptance.
Yes.
So if we're doing a template fit, well, all you need is this change from particle or parton to RICO as a function of EFT. But then is it easy for anyone else who is not in the experiment to replace them? I mean, these information encode detector knowledge that depends on what you put in, right? I mean, if you put in a different EFT, you will get a different response. I don't know if I've conveyed the point. So what is useful for you to get? This is from the experimental point of view.
Yeah. So I mean, I think for now the best interface is a rivet routine. So it is not for detector level, but at least to the particle level, right? So we avoid the unfolding to parton level, and so if the experiments would consequently provide rivet analysis, that would help already to mitigate at least the model dependence on the parton level unfolding. That would be already, I think, a good step. There are already some rivet analysis available, but it would be nice to do it more more rigorously. Apart from that, I mean, I'm not sure if it's feasible, but if the experiment can do what you just said, to do basically an analysis not on the basis of the standard model, but with EFT contributions, and then basically include this in the final likelihood, and then provide actually the likelihood as a function of the Wilson coefficients. That would be most helpful, right? Because then you can just, as a global fitter, you can just take the likelihoods and combine them. I mean, if that is feasible, but I imagine it's really complicated because, I mean, I guess you rely on huge Monte Carlo samples, and then you have to sample the parameter space reliably, and to get enough points to do interpolations and stuff like that. So, I mean, in the Wilson coefficient space. So, yeah, I mean, if it's feasible, it would be great, but maybe one has to restrict oneself to the most important operator. So, for example, that also goes for the background, right? I mean, what about operators that contribute to the background? So, first of all, one has to determine which are really the ones that we worry about, which have most impact, and then maybe concentrate on that. Probably it's not really feasible to do a 20 parameter likelihood for all the analysis, but maybe with some important Wilson coefficients. It's definitely the ones that go also in the signal. Was it helpful, or?
Yes, definitely. I mean, this is food for thought. I think we need to discuss these aspects more, because.
Yeah, sure. I mean, there's this new LHeC working group, right? I'm not sure what this is.
LHeC EFT working group. Yes, Atlas has and CMS have representatives in there. It's being formed.
Yeah.
representatives are being appointed. We already know the names, so things are moving.
Yeah,
But the LHeC top working group is also the place where we will also want to discuss these things. So yeah, the boundary between these two groups is not yet established, but we need to find collaboration for sure.
Yes, thanks, Francesco, for making this comment. Indeed, a lot of work already started within the LHeC top working group. Maybe you are aware of this. And with this new LHeC EFT working group, we just want to reinforce the activities from the top side there.
Yeah, I noticed there's also a recommendation from the, how it's called, the Forum for Reinterpretation of LHeC Results. I think they have also some helpful hints in how to provide useful experimental data that contains as much information as possible, given that you have some kind of constraints on what kind of information you can release, but at least as much as possible. So I think it's also worth looking into there and folding this into discussions on how to proceed with the representation of EFT usable results from the experiment.
Thanks.
Any further comments concerning this, or any new questions? Perhaps also to other speakers? We still have 3 minutes, so let me ask a very naive question to Peter. Actually, you were talking about the top-quark decay, and on one of your slides you showed this this combination of the cross section and the width in an arrayed approximation. And at this point, you said that you simply need to combine those. Is the combination of these two trivial? I mean, aren't there some operators that enter both that would be correlated? I mean, is this easy to do?
Yeah, I mean, okay. At that point, one doesn't really. I think one doesn't really worry about the correlation. I mean, it's just you want to have the value of the decay cross section at a point in Wilson coefficient space. And now you just calculate the numerator, which is a multivariate polynomial, and you calculate the width also as a polynomial, and then you just form the, I mean, you just calculate it, right? I mean, and then you have the value for the cross section at that point in a Wilson coefficient space. So that's what we do, and we have also checked that this works. So basically by generating or by calculating the parameter point with this method, or with just using really a new event sample which is a dedicated at that dedicated point, you know, and then just calculate and just comparing this the two results, and it works. I mean, within the narrow width approximation. Depends, of course, on what observables you look, but if it's valid in the narrow width approximation, then it works.
So it's not a limitation in any respect, and moving into fully offshore calculations would not provide much, except perhaps sensitivity to processes that mix and interfere, I guess.
Yeah. There are some phase-space regions and some observables that you probably cannot access with this approximation, and there you would need a full offshore calculation, which is by the way also available via MCFM. But then I think this is not. I mean, then you really have to sample you have to find something more clever to sample the parameter space, I think, because it will not be the polynomial structure anymore.
Okay. Okay, thank you. I would like to thank all the speakers again for their nice talks, everyone for asking nice questions and stimulating very useful discussion. I suggest we break for coffee now, and we should reconvene at 11:35. Thanks again to everyone, and I'll see you soon.
Thanks.
If anyone wants to check their share screens, you could do it now for the next session.
Yeah, I see Adrian, Daniel connected, and Kacper as well.
Can you hear me?
Can you hear me? Yeah.
Okay.
Yes, we can hear both of you. Can you try sharing screens and videos and all of that?
Okay.
With the Hello? Sorry.
Hello?
Yeah?
I'm trying to share. Can you see?
Yes, we can see.
Okay, so if everything is all right, I stop sharing.
Yeah, can you just browse the slides that everything works?
Okay.
Yeah, excellent.
There is only a black box at the top. This is probably the Zoom window. You have to move it further apart, I think, or minimize it somehow. Because otherwise it's
I'm trying to do so. If you have any hints how to hide this bar, it would be very appreciated.
Okay, or at least move it to the very top as far as you can.
No, you can stop share and share the full screen.
Oh, okay. So I will
share the desktop.
Okay, so is it everything all right? Okay now?
It looked the same to me as before, but
yeah, there is still a line at the top, but it's only the 1 centimeter at the top, so it's probably okay. No, now it's bigger.
I know it's because I'm trying to find some settings so it opens up.
If you share, you can try to share your entire desktop, not the application.
I'm sharing right now my entire desktop, so I'm not sure how.
Okay.
Well, the question also is whether there is any important information hiding in that.
No, there is like at the top. There's usually only the faculty logo and cooperation. So I hope that this won't be a problem.
Okay.
So worst case scenario, you get a complaint email from your university.
Yeah.
Okay, I will try it myself. First. Same screen. You see it?
Yeah, that looks great. Yeah.
Okay.
Thank you.
Later.
Please also remember to switch on your video when you talk. In case the bandwidth is not sufficient, I will just switch it off for you.
Can you see it?
Yeah, we can see it. Great. Thanks.
Okay, perfect.
So we tried with Kacper and Adrian. Is Daniel around? maybe we just try 3 minutes before we come back. I will now go for a break. Thanks.
Okay, thank you.
Hello, do we have Daniel connected? Daniel, if you can hear me, if you're there, it would be a great time to try your audio and sharing of your slides.
He is connected, but I'm not sure he's presently there.
Yes, it seems so, yeah. Hello and welcome back to our fourth top and electroweak physics parallel session. My name is Soham Bhattacharya, and I will be your chair for this session as well. I remind you that behind the username top-quark and electrophysics, there is a real person hiding. His name is Sasha, and he's our Zoom technical assistant. So if you have any difficulties, please turn to him through chat. In particular, he's ready to share your slides if you would rather not share them yourselves, or if you have any difficulties sharing them yourselves. At the moment, we have 17 participants connected. Great attendance. Thank you everyone for connecting. And we will now have 3 talks, each 18 plus 7 minutes, followed by a 10-minute discussion session. Immediately after that, there is a topical discussion session scheduled, so please don't leave. The topic of the discussion today is electroweak precision. And yeah, I remind you all to mute your microphones when you're not speaking. When you want to speak, please switch on your video and start by saying your name. If you do not have option to use your video, consider uploading a recent picture of yourself into your Zoom profile. And we should have plenty of time for discussion, either right now, right after the talk, or in the general discussion session at the end. So please don't be shy. If you want to ask a question, raise your hand if you can and know how to. Otherwise, just unmute yourself and speak up. Feel free to also post questions into Zoom chat and the Mattermost channels if you cannot speak. I suggest we start with the talks now. Our first speaker today is at this session is Kacper. Kacper, are you ready? Can you?
Yes, I am. Can you see my slides?
Yes, we can see your slides. Thank you.
Sure. Okay, so can I start?
Yes, please go ahead.
So hello, my name is Kacper Nowak, and today I will present you our work on optimizing top-quark per production threshold scan at future E+ E- colliders. I will start with briefly describing our motivation. So the threshold scan is assumed to be the most precise way to determine top quark mass. Baseline scenario assumes taking 10 scan points with 10 inverse femtobarns in each. The dedicated study for LHeC shows that the precision of such measurement is around 20 megaelectronvolts. However, this is based only on two-dimensional mass and width fit. So all other parameters are considered fixed, so like we knew them with infinite precision. So it's not quite a realistic assumption. What is more, threshold cross-section depends also on other model parameters, such as top-quark Yukawa coupling and strong coupling. So we wondered how it influences the top-quark mass determination precision, and also can the scan procedure be optimized? Now I will describe our fit method. We start with generating a set of cross-section templates using QQ-bar threshold software. For each of those templates, we assume different set of top-quark parameters values. In this way, we obtain a grid of templates to which we can later use to compare our pseudo-experimental results. We also incorporate luminosity spectra, which we use to take into account parameters, the spectra that are specific to each experiment. We use spectra from LHeC, ILC, and FCC-eh. But our main spectra that we use for most of the for almost all of the results, unless I will specify otherwise, were those for LHeC. As a benchmark scenario, we assume taking 10 measurement points at the threshold with 1 gigaelectronvolt step between each one of them, with 10 inverse femtobarns taken in each one of them. To simulate experimental environment, we generate statistical fluctuation, assuming 70.2% even reconstruction efficiency and background level corresponding to 73 femtobarns. Now, when we have our pseudo-experimental results, we can compare it with all other templates in the grid. And by compare, I mean calculate chi square values. We assume that there is quadratic dependence between chi square value and the model parameters. So the points that we obtain in this way, to them we can fit a parabolic surface and thus obtain all of its coefficients. From those coefficients, we can extract the position of its minimum, and so the values of top quark parameters, and also estimate uncertainty by cutting this paraboloid with a plane corresponding to delta he equal to 1. As this process involves generating random numbers, sometimes the fit doesn't converge, so we remove such bad results by looking at fitted values, and if they are outside of range that were used to generate templates, those results were ignored. Now I will show our baseline fit results. We start with looking at different configuration. We started with a two-dimensional one, similarly to the LHeC study, taking into account only mass and width. All other parameters were fixed. So as you can see, when we know normalization to sub% level, we can expect statistical mass uncertainty to be around 20 megaelectronvolts. So it's a good match with the LHeC study. However, when we add more parameters, such as Yukawa coupling and stroke coupling, the mass uncertainty raises significantly. When we consider all 4 of those at the same time, the best we can do is around 70 megaelectronvolts, regardless of how well do we know normalization. However, this approach is also quite unfair, as previous experiments have already measured some of the top quark parameters with a given uncertainty. So by using this knowledge, we can improve our results. As you can see here, by constraining one of those parameters in the most general approach, we can get our results very close to those where these parameters was fixed. As you can see, for example, for 4D fit with Yukawa coupling constraint. Those results are very similar to the 3-dimensional fit with these parameters fixed. However, when we constrain both of those parameters on the most general approach, those results are quite far from those that we obtained from 2-dimensional fit. So we wondered, how well do we have to know those two parameters in order to get our mass uncertainty close to the 2-dimensional fit, so around 20 mega electronvolts. Here you can see a heat map of statistical mass uncertainty. To obtain results with mass uncertainty around 25 mega electronvolts, we have to know at the same time Yukawa coupling with precision of around 0.1 and strong coupling constant around 0.005. Similarly, we can do this for Yukawa coupling to see its contribution to the top pair production with uncertainty of around 0.2, which is represented by the black isoline. We have to know normalization around 1% and Yukawa strong coupling around 0.001. We also wanted to investigate how different luminosity spectra were influences our results and also how it changes in luminosity. So we changed just the luminosity spectra. We assume the same background, the same efficiency, and no polarization. As you can see, the best results can be obtained by FCC-eh, as it has almost no tail in its spectrum, so it shows that it is quite a significant improvement. However, this is a very basic comparison and it's not anyway decisive. Now I will proceed to our scan optimization procedure. We decided to use genetic algorithm, which implements the concept of survival of the fittest. So we have to some kind of genotype that are some kind of variables, and they code for a phenotype, which is a set of measurable traits that we want to improve. We assume that each of our measurement points makes a chromosome, so entire scan sequence makes a genotype. We assume that total luminosity is always 100 inverse femtobarns and is equally distributed between points. So from our genotype, which is scan sequence, our fit procedure can create phenotype, which are top-quark parameters uncertainties that we want to minimize. So based on this criteria, we can choose most fitted individuals to multiply them to create some offsprings and choose them for the next generation. And to create new offsprings, we take both parents' genotype and randomly choose their parts. And for each one of those chromosomes, we allow to add random mutation in range from minus to 0.5 to plus 0.5 gigaelectronvolts. We also add 5% chance to drop or gain any new measurement points. So in this way, we can also optimize the length of the scan sequence. So it might be shorter or longer than the original. We optimized our scan sequence first for mass and width. As you can see, on the left side, there is the green dots are representing the reference scenario, and the blue dots represent the last generation that is finally optimized. And there is quite a significant improvement in both mass and width. For width, the statistical uncertainty can be reduced from around 66 megaelectronvolts to below 55. For mass, it's from around 36 to 28 megaelectronvolts. So it's around 25% improvement for mass. On the right side, you can see histogram of measurement points from the final generation. You can clearly see that they are grouped into 3 regions on the threshold, one slightly below, one in the middle, and one above. So this plot shows where are the regions that are most sensitive to those 2 parameters, and where should we focus our measurement in order to obtain the best results. We also run optimization procedure for mass and Yukawa coupling. The results for mass is very similar as before. However, for Yukawa coupling, there is very little improvement. So as you can see, it's around 10%. But when we look at the measurement points histogram, it gets quite more interesting, because there are still those 3 regions that you could see before, but now the 4th one appeared. So it shows that we need those 3 basic regions that were also present in the previous slide to measure mass and probably with a good precision. And the 4th one appears in order to have a good measurement of the Yukawa coupling. So in this way, you can even identify which regions are necessary to measure which parameter. However, it's also quite clear that to measure mass with a decent precision, we have to know also something about width. So it's also a very interesting conclusion from those plots. To compare that what our procedure gives us with our reference scenario, we chose the best scenarios from both of those optimization procedure. As you can see, for mass and width and mass and Yukawa, there are pairs of points in each of regions that were seen of the measurement points histograms. This shows that it's quite that those regions are really especially sensitive for those points, and there is only point measuring in them. We generated around 10,000 repetitions for each scenarios in order to obtain each of those points. And as you can see, when we comparing them and with changing luminosity, that our optimized scenarios lower the statistic mass uncertainty by around 25%, which is corresponding to the increase in luminosity by a factor of 2. So in order to get the same results as our optimized scenario, reference scenario needs luminosity of around 200 inverse femtobarns. We also ran our optimization procedure on all 3 of our spectra, so also for ICHEP and FCC. And the results are quite similar in this term of improvement, because we get for all of those experiments around 25% of mass uncertainty reduction. And the behavior of those new scenarios are very similar for them, as the FCC also gets the best final results, are even below 20 mega electron volts. However, as mentioned before, we assume the same background and efficiency and no polarization. But the FCC and ILC gets also very good results. So now coming to the conclusions, the top quark mass can be extracted with statistical uncertainty around 25 mega electron volts, even if we consider the most general approach. But we have to know parameters with a given constraints. For scan optimization, we have shown that it is possible to reduce statistical uncertainty of top quark mass by 25% for all planned experiments without losing precision in width or in Yukawa determination. And we also hope for some further improvement when we take into account polarization and other observables, but we are still studying it, and we hope to publish our results soon. So thank you for your attention, and if you have any questions, I will be more than happy to answer them.
Thank you, Kacper. Thank you for this very nice talk, and thank you for leaving plenty of time for discussion. Are there any questions? Yes, I can see a raised hand from Uta.
Yeah, so thank you. Perhaps I didn't understand it carefully enough. For your luminosity plots, if you go back, I think, yes, yeah, any of the slides. Yeah.
Oh.
Yeah. So for your final results, are you assuming this per beam energy, this luminosity of 600? Or at least 200 inverse femtobarn, or is it the integrated luminosity that you need
I think with integrated luminosity.
For all, so that each of the scan points, yeah, so that here you have quite a lot of, perhaps you're too fast.
Yeah, sorry, I was quite confused that I thought you meant.
Any of those plots, so that if you go here, for instance, to 600 inverse femtobarn for the green line, this is then integrated for all scan points.
Yes.
It's not for each of the scan points.
No, it's always like we assume that the total luminosity of our scan sequence is always, let's say 100, and when we scale it higher to 600.
You just scale it so that, but what would be interesting is somehow the times that are needed, for instance, for each of the plus and minus colliders to collect this, because there are, of course, time-dependent effects, which may, because if you need longer time to get this, and if you need longer time to do the beam scans, there may be, of course, additional time-dependent effects, which may add up here in your normalization uncertainty. Do you have an idea how the times would compare between the different colliders?
Sorry, but we are our comparison between colliders is actually very basic, only on the luminosity spectra focused. So this was the only parameters between experiment that we actually changed.
Yeah, but I think it would be interesting. Yeah, for instance, if this would mean 3 years for the one and in just a few months for another, I think it may be interesting to know.
No, I mean hi, Uta, this is Roman. I mean, I think 100 inverse femtobarn at the ILC, assuming that the collider runs, of course, takes half a year max, and it takes the same time as at other colliders, and maybe even a bit longer at other colliders, because that's the part where the luminosities start to cross each other, this TT bar threshold. So this is comparable basically at all collider options. So let's say half a year plus some tuning, so a year.
Thanks, Roman. Yeah. Then it's just the advantage that the FCC-eh would have 2 interaction regions, which is, of course, important for cross-check systematics, not just for completeness. Yeah. Okay, thanks.
More comments, questions? If not, I have a question. I forget to note down the slide numbers, but when you show the energy profile of the threshold, basically, if you can go to one of those slides.
Like at the beginning, so
yeah,
like,
at the beginning, it's fine. Yeah,
like this slide, or
yes, that's fine. So I saw that you're using a code that seemed to only include top pair production, but there would be a contribution from a single top production in this case as well, I guess, at T plus E minus. Was this studied anywhere? Or is this something that you may consider including for, sort of a better description of of this profile?
I think we will have to look into this when we'll be expanding our present analysis. So because we are right now only focused on the pair production.
Okay. I think there is a calculation from Wizard which includes fully offshore calculation, which as a consequence would include a contribution from TW associated production. I'm not entirely sure what kind of threshold effect they include.
So if I could comment, here's Filip Żarnecki from Warsaw.
Yes, please.
The single top production is what contributes to the background, which is taken into account in this study, but assuming it's flat. So this is what clearly should be improved. So at the moment, we just take the estimate of the background, which was previously obtained, and we assume it's flat over the threshold scan region. And okay, this is a simplification, but at least it's taken into account partially into the statistical
I think the role of polarization has maybe to really carefully looked at, but you can also be very blunt saying, I work with right-handed electrons, and then off, you are done. You don't have it.
Right.
Switch it off. But there may be other consequences, but a priori you can switch it off, at least at linear colliders.
That's great to know. Thank you. Any more comments or questions? If not, we still have time for one more question, and I have one more question. So in your optimization procedure, if you now could skip to those, yes, these exactly. So this would be a profile for a fixed width and mass, right? The right thick curve, or does this include variations of mass and width? What is not entirely clear to me is how this position of those points that you get out of your optimization procedure depends on the actual truth top mass and top width that you're trying to measure, i.e. to what extent can you really use them if you do not know the value of the mass and top width in advance?
They are quite useful because for those results used here that we use with new generated scenarios, we actually drawn the true top quark mass value from a normal distribution, I believe with a width of around 200 mega electronovolts. And there was, of course, the results were a little bit worse, but in fact, by the fact that our new scenarios are made of points, of pairs of points that are slightly separated from each other, this change of true value of the top quark mass is not so critical for ours. Of course, if there is a huge mistake, like let's say by 1 giga electronovolt, it's of course it makes our analysis significantly lowers our mass determination precision. However, for small changes, like as I said, from drawing from normal distribution with around 200 mega electronovolts, so there was no significant effect for any of our optimized scenarios.
Right. So assuming that at some point LHeC will know the top quark mass with 200 MeV precision, this is I mean the conclusion that you come to that these points are the ones that have really high sensitivity is actually a very powerful prediction, right, for you?
Yes.
Okay. Excellent. Thank you.
So,
any more quick questions or comments? If not, I suggest we move to the next speaker. Adrian, are you ready? You're muted.
Yes,
oh.
I'm ready.
Okay, excellent. I'll let you share your slides and then just start at your convenience.
So, can you see them and myself?
Yes, we can see you and your slides very well. We can hear you as well. Thank you.
Okay, so yeah. First, thank you for this opportunity to present in probably the first virtual conference of the ICHEP. Yeah, I will present the report on the heavy quark production in high energy electron-positron collision. And well, I will focus mostly in the experimental case of the big quark, but I will also talk a bit about the top quark and the C quark. And I will focus in ILC case more in the 250, but including also some conclusion from the 500 GeV program. And most of this, well, all the studies have been done within the ILD framework. So I have a couple of slides introducing ILC and ILD. I will not go to the details. Sorry. I will not go to the details because this has been explained in several talks before. I have a list of talks here and a few of the main aspects that are important for us that I will not go to the details, but basically saying that the ILC is able to explore or have access will have access to all standard model particles because the program foresees several energies of running the full program. For linear colliders, the center of mass energy can be tuned or can be changed with quite easily, let's say, and can be upgraded. And we also have the possibility to have beam polarization, and ILC foresees to have polarization for both the electron and the positron beams. So about the ILD, again, the same. I will not go to the details, just have here some of the highlights, a snapshot of what is ILD, and just saying that we rely, especially for this analysis, in excellent tracking and secondary vertex reconstructions with the first layer at already closer to 2 centimeters of the beam pipe. We have high granularity calorimeters optimized for particle flow, also together with the tracking system, and we foresee to have a TPC that will allow for particle identification, hadron identification, that is very interesting for our analysis. So again, you have here a link to the talk of ILD from yesterday. So what is the motivation? One of the motivations for these measurements, we know that the effective angle was obtained by LHeC and SLC in the past from 2 independent measurements, different measurements, but we observed that there is a tension between the estimation of this parameter that contradicts the fit of the standard model, and it is not clear if this is a real effect associated to heavy quark effect in physics, or new physics affecting all quark or fermions, or it is just statistical or experimental fluctuation. So to resolve this issue, we are required to measure this with these parameters with observables having the per mil level of experimental precision. A bit more on motivation. I will not go to the details of many beyond standard model scenarios. I think with the talk of previous talks, we have an overview of all this. But basically, there are many beyond standard model scenarios implying Randall syndrome, composite Higgs unification models, etc., that predict heavy resonance coupling especially to the top and B quark, but also some of the models predict couplings to all fermions or to lighter fermions like the C and the S, or even all the fermions. This resonance tend to couple to right components, and as I said, this is a list of possible models, and you can find many others. These are just some examples. And what do we need to prove these BSMS scenarios? Again, we need experimental precisions of the per mil level, and can we do it? And this is what I will describe in this talk, focusing in the BB bar case, which is in the middle of TT bar and CT bar in terms of mass. For that, we need to look at 2 fermion processes, and this is a simplified description of these processes, in which we see the differential cross section for the two polarizations of the beams, in which one with left polarization for the electrons and right for the positrons, and vice versa. And we see these terms that are called helicity amplitudes, which are the terms that contain the couplings or the form factors or the Wilson factors, or the notation that you want. These amplitudes are independent, are characteristic for each fermion, and only beam polarization allows to inspect the 4 of them. So these processes have been deeply studied at LHeC and SLC at the set pole, which is a completely different framework in which we don't have access to the set, to the gamma or the interferences. And also we had moderated quark tagging and acceptance of the detectors. So in this slide, I showed you a summary of what are the expected cross sections for different processes at 250 and 500 GeVs with polarized beams and polarized beams. And basically what I want to show you here is that the beam polarization enhanced is not only allows to have access to the different helicity amplitudes, but also enhance the cross-section values. And as I said before, I will concentrate in the B quark production at 250 GeVs. So what are the observables that we need to reconstruct to measure? This is a summary slide where we see the most common observable, basically inclusive cross-sections, ratios of cross-sections at the set pole or measured at high energies, differential cross-sections, and asymmetry. Most of these observables are normalized, which helps a lot for the experimental studies. And some of them require the tagging of the quarks, but some of them require also the charge measurement to measure the angular distribution, for example, these two here. So this type of analysis requires the full detector, the comprehensive study of the full detector, because we will need to reconstruct jets, leptons, and all emitting energy. But there are two features which are key for this kind of analysis, which are the flavor tagging and the charge measurement. The flavor tagging is indispensable for all analysis, from the S-quark to the top-quark, because we really need to tag the production of these two quark. And the quark charge measurements is very important for the top-quark, because we can use the charge measurement of the big jets producing the decay, or even the W decays hadronically, but it's indispensable for the analysis for using with BB bar, CC bar, SS bar in the final state, because this is the only way to measure the direction of the quark, of the produced quark. How do we measure the charge? Basically with two methods: the vertex, measuring the charge of the vertex, or by measuring identifying kaons or in the final state, which carry the information of the charge of the big part, for example, of the B meson. So these methods are highly efficient, will be highly efficient, highly pure. We will see this later, and in principle, all future detectors can base their measurements in these techniques. So this is a bit of the starting point of the analysis for the B and the C quark. I have here, basically what we have is our topology in this event is back-to-back topology. So we have two jets which are back-to-back, more or less. And the main source of systematic that we had at LHeC and SLC was related to the tagging efficiency, and to have high precision in this tagging efficiency, we need to measure this efficiency and not rely on Monte Carlo if we want to reach the per-mil level accuracy that we want to reach. At linear collider, we have new sources of uncertainty, like the beam polarization or the event selection, but because now we have backgrounds which can be dominant if we don't remove them, like, for example, the radiative return backgrounds. That can be up to 10 times our signal. So in order to measure the efficiency of the tagging, we need to use, we can use the double tag method, which basically at LHeC, which basically consists in the comparison of two samples of events, one with single tags and one with double tags. At LHeC and SLC, this was very easily done because you don't need to do a pre-selection, basically to remove, you only need to remove the lepton decays. And this is a simplified formula of this approach, of this double tag method, in which we see the two samples, and then we see that this the number of events or the ratio of these events depend on efficiency, P efficiencies, or miss efficiency, the C and the UDS, and the inclusive ratios RBRC and UDS. And we also have the correlation factor. So we can measure most of these factors, or except the correlation that we have to rely on Monte Carlo, and depending of our tagging efficiency, we have to rely on Monte Carlo, or we can measure the miss efficiency that we expect that we can do it in ILC. I will not go to the details of this in this talk. So what do we need to use this double tag is first a pre-selection that provides similar efficiency for all quark flavors. We see that we have this for the ILD. We will have it. And so for both polarization, we see that we have all the selection of all flavor of all quark flavors are basically the same with very small differences, and even more important, is very flat in all the detectors except in the very forward region. We also need a pre-selection that reduces the mean to the minimum the main backgrounds. As I said before, our main background is the radiative return, which is 10 times larger than the signal, and but in most of the cases, this the associated photon is lost in the beam pipe. So we can filter these events by looking at the reconstructed energy using angular or conservation arguments. But there is a remaining 10% in which the photon is inside of the detector, and then to remove this, we need to filter these events by identifying photons in the detector with high efficiency. We can do this with more than 90% of efficiency. And at the end, our background, our signal is very, very small. And we can see this here. We have a very small amount of background remaining in our sample. So also for this method to work, we need to have high quark tagging efficiencies and minimal mistagging efficiencies. Don't show it here, but the mis efficiencies are very small. For the C quark, we have lower than 0%, and the UDS is basically 0. And what I saw in the left plot are the efficiency of B tagging in red. We see that it's very flat in all the detectors, is larger than 60%, and we have a drop in the forward region where we start to lose tracks for the vertexing. And I also have here the efficiency of the charge measurement method. So this implies the tag plus the charge measured by using the vertex method or the Keon method. And again, we see that this is still quite large, and this allows for double tagging methods. And in the right plot, I saw for the same categories, what I saw is the correlation factor that we see that is basically 0 for all the detector and is constant, except in very forward region in which we start to have effects due to the difference of the gradient of the efficiencies. And just to compare, this value was at 2% of LEP, and this is a large source of uncertainties in this analysis. So once that we have done this, we measured this efficiency, well, we can calculate the charge of our jet and calculate what is the angle of our jet, of our BB bar system. But even if we are highly efficient measuring the charge, we can. It is possible that we measured it wrongly because we miss a track, and that flips the sign of our B meson, or the Keon is wrongly identified and it was a pion, or we have also B0 oscillations that flip naturally the charge. So this produces a change of our angular distribution. One event that was in positive angle goes to the negative angles, and vice versa. And as we have very large asymmetries for the BB bar case, especially in the left polarization, these flips of change are visible and can be confused with the new physics. This is what we see. This is the difference between the dashed line and the histogram. So we have developed a method to basically correct for these migrations by basically calculating the probability of reconstructing the wrong or the right charge using a similar method that I explained before, using a double tagging method, that we can use the data to calculate to correct for this migration, to calculate this PV, this probability, and correct for this migration. And this is what we see where we look at the comparison between the blue points and the black lines. So we apply this method, and then we have the results for the right-left polarization and the right polarization. And this is what we see between the red points and the red points, and the green histogram is the parton level distribution. And we see that we have a very nice agreement, especially in the barrel. And then we start to have some drop of acceptance in the forward region that we can correct easily. And then this is the correction that we observe. And with the correction, we have a perfect agreement between the green and the blue. Anyway, this analysis is all the results that we have from this analysis are constrained to the angular cosine theta lower than 0.8 in absolute value. So the corrections for these acceptances will be minimal in the final result because they only affect 1, 2, or 2 beams.
Excuse me, you have about 3 minutes left. Thank you.
Okay, so these are the results that we have, the expected results that we have for the different beam polarization expected are ILC. We have here the breakdown of all uncertainties. And what we see is that we can reach the Fermi level of precision. So these results, these precisions in the observables can be translated in the precisions that we can get in the couplings. And this is a notation that we have, simplified notation that we have in the left plot, in which we assume new resonances, basically Randall-Sundin resonances. And what we see is that first, in the right part of the plot, going to the gigaset program, using the gigaset program, we can improve LHeC measurement by a factor 10. We can resolve the LHeC SLC issue, and we will get a very Fermi level of accuracy in the couplings in order to inspect new resonances. This plot can be also constructed or using benchmark models. The models are described here as the same that I described very briefly before. And we see that we have very large power of discrimination of these models. We have in the red what we can do at gigaset, and then the different couplings, and what is the power of discovery of new physics with inspecting the different couplings. I have here a column for the C-quark case, which is not explained in this talk, but okay, you can see here. And the main point is that we have having access to thanks to the beam polarization, we have access to all these right couplings, which are the most powerful in order to discover new physics. And we will have access to resonance of the order of 20-30 GeV already at ILC 250. So I go quickly to this. This is the summary or the top-quark. The top-quark is more involving because we have more complicated topologies. And what I saw here is for the left polarization, the angular distribution for the top, and for the big quark from the decay. We see that we have nice agreement between the expected and the reconstructed. We see again the drop of efficiency in the very large angle for the big quark. And okay, these are studies for the total luminosity forcing for ILC. We will have, again, we expect to have precision, statistical precision of the order of similar to what I presented before. And we expect that these systematical uncertainties will match the statistical precision, but this is true that we need to solve this. And it's important thing is that these plots are for the semi-electronic case, but we can also study, and we are going to study hadronic case, because the BJet and the W hadronic decays carry a lot of information about the charge of the top quark. And these are results comparison between the ILC, LHeC, and some of the results of FCC for 500 GeVs ILC and 365 FCC. We see that in both cases, lepton colliders are much powerful than LHeC measurements for this kind of measurement. We see that, well, the FCC assumes that it's measuring the polarization of using the final state, not the initial state, but it also can be done at linear collider. And as a remark that being far from the threshold at high energies, the axial coupling, its measurement of the axial coupling is improved in linear colliders. And this brings me to my conclusions. Sorry for being late. Basically say that the ILC will have the answer whether the new physics acts on the heavy doublet or even in the all fermions, because we can access to the C and the S bar. We will probe the helicity of the full helicity structure of the electro-weak fermions with experimental precision of the Fermi level. It is a very demanding analysis, and I hope I convinced you that it is possible at the ILC, especially at the big quark, which I made more emphasize here. And we hope that if there is new physics, we know that it will be already visible at 250 states of the ILC. So that's all. Thank you for your time.
Thank you very much for your nice talk. Are there any questions, please? I don't see any hands.
If I may, but it seems I cannot raise my hand. On slide number 16, you were talking about using the probability for the track reconstruction for the different tracks here, the PB. And you said you're going to measure this in a data-driven way. Can you say a little bit about how you plan to do this?
Yeah, so this is basically the probability. So we will measure the charge using the vertex. We reconstruct the vertex and we look at the charge of this vertex. And what we don't know if this was the real charge of the big quark, or it is fleet because we have lost the track, or because the beam meson has basically oscillated. So what we will do is we assume if we assume a high probability of having the right charge, we can assume basically a binomial probability. And what we do is to measure events in which both jets have the same charge measured, which is obviously wrong. One of them is wrong, or both are wrong. And events in which both jets have different charge, in which we are possibly making the right measurement for both or the wrong measurement for both. And playing with these combinations, we can basically measure the PV value. And then we can apply to correct for the wrong measurements.
Okay, great, thanks. So similar to like same sign, opposite sign measurements in, let's say, electrons on the Z peak. Okay,
yes.
Thanks.
Thank you. Any more questions? If not, I have one naive and quick question. On your slide 19, so that's your sensitivity to various couplings that are specified on a previous slide. In there, this LE, LB, okay.
Yes.
So the size of these couplings seems to be rather large. At which point, I mean, can you compare them to like one of these perturbativity limits? At which point do these couplings become non-perturbative? Do you have any idea? I mean, do you have access to the region where these couplings are perturbative, in other words? So, you know, comparing it to, because it's hard to see for me the normalization that's taken out of this. And normally you would compare it to something like 4 pi, 1 over 4 pi or something like this.
Yeah, so these are really leading order estimations, assuming, I think, masses of several or the order of 10 tera electron volts for the models. And yeah, so this is a preliminary estimation, and I agree we have to introduce this in a more formal framework in order to extract the...
Yeah, sure. That's fine. I was just curious. Are there any further questions? Comments? If not, thank you, Adrian, again for this really nice talk.
Thank you.
Thanks everyone for questions, and we proceed with the next speaker. Daniel, are you ready? In case you try to say something, we can't hear you or see your slides.
Now you can hear me, right?
Yes, now we can hear you.
I
Excellent.
cannot see anything yet. That's just a second. Yeah. I'm looking for here. This is not the right one. No, I cannot select the window.
Perhaps you can try to just share the whole desktop. This seems to be the preferred choice for many people.
Yeah, so do you see it now?
Yes, we can see it.
Very good.
If you can also switch on your video, that'd be great.
Yeah, just a second. Yeah. You can see me, right? So hi, yes, I know it's here. Hi, very good.
Excellent. Hello.
Okay, my name is Daniel. I'm presenting on I need my slides. I don't have them open here. Now I have them. Top electro-weak physics at LHeC. I know top and electro-weak both are mainly subjects in E+, E- or in proton positions, but there's also electron-proton. And I present you now prospects for future measurements in electron-proton. So when we talk about electron-proton colliders, we talk about deep inelastic electron-proton scattering. And then we have basically 2 or 4 dominant leading order processes. This is a neutral current exchange where we have a photon, a gamma Z interference term, or Z exchange.
Sorry, Daniel. Let me. Sorry, but I think I have to interrupt you because there is a quite a chunk of your slides on the right-hand side that's not displayed.
Better now?
Yeah, that's perfect.
Okay.
Thank you. Please
so
go on.
neutral current charge current exchange. Yes, okay, you know about it. Charge current is mediated by, of course, the W boson. Typically, people do QCD because the Z on the W are color neutral particles, and one can directly probe the dynamics of the proton and of the QCD bound states. I'm now interested in basically in the gamma Z W exchange terms, and also in the hadronic finite state, which can also, of course, include a top quark or a Z or W boson produced directly. So let's talk about first about the experimental setup. We proposed to upgrade the LHeC in the 2030s with an electron beam. This is based on an energy recovery LINAC technology, which surprisingly got the highest priority in the European strategy update recently. And this is really a groundbreaking new technology because it really extends the possibility for an electron collider or an electron accelerator in terms of current and energy with respect also to the power consumption. So basically, we propose a high energy accelerator with about 50 or 60 GeV and a very, very high current, which means that we can also record a very large amount of integrated luminosity, and we expect that we have 1,000 inverse femtoband recorded within maybe 10 years of data taking. So only yesterday we have uploaded the update of the CDR to archive. So in 2012 it was already a first CDR, but this time the Higgs was not discovered, and also the technology for the electron accelerator was not yet clear. So this has now been decided, and lots of things have happened, and now we've updated also on physics studies. These are, of course, very, very rich in the new experiment. And I'm focusing on electro-weak and top-quark physics in this talk, and also to some extent on the impact of of the LHeC on precision measurements at the high Lumi LHC in the future. Starting first the kinematic plane, so we have the Q square, which is the form momentum transfer of the exchanged boson. It's a function of x, which is the momentum fraction of the incoming parton. And then we have over all the kinematic plane, we have very, very, very rich physics program, which is also presented in many other talks in this conference, so on BSM, on Higgs, on heavy ion physics, a very, very rich QCD physics program, of course, and also in the CDR we have technical outline of the future facilities, which include the detector description, which was presented in the detector session, and also on the LHeC accelerator and on the PERLE, which is the demonstrator project. And I'm now focusing on top and electro-weak physics, which is, of course, at higher scales and also at higher X. Coming first to top-quark production. Here, 5 channels are altogether very important. The 2 most important ones are single top production. On the left, in charge current DAS. So here we have a cross-section of 1.9 picobarn at the LHeC. And the other important channel is top-quark pair production in neutral current exchanges, basically photo production, where you have a cross-section of 0.05 picobarn. And in DAS, this is 0.02 picobarn. Of course, with this single top production cross-section, one has direct sensitivity to the CKA matrix elements, to the VTB coupling. And there was a study performed in the full hadronic decay channel of the W, together with a cut-based analysis, with a simplified detector simulation, also including backgrounds. And after a careful analysis of this pseudo data, one expects that one can measure this CKA matrix element without any constraints on the unitarity of the matrix, with 1% precision, already with 100 inverse femtobarn. While of course we know that we expect nowadays already 1000 inverse femtobarn. So this would be even better if we finally have data. Compared to the present best measurement, it's about 7%. So this would considerably improve, of course, with respect to our nowadays knowledge. Then one can also introduce anomalies couplings. So these are the vector couplings and the tensor couplings. So 2 is the tensor couplings, left-handed, right-handed. 1 is the vector couplings. And similarly, with F1, of course, case with VTB. So here one has a 1% precision as a function of the integrated luminosity. The others are less precise, but also still in the percent up to the 10% regime. I think this is also very precise measurement. In the neutral current sector, the most interesting parts, of course, the search for anomalies favor changing neutral current coupling. So these are suppressed in the standard model, and only in higher orders are included. And naturally, if one thinks about the photon or Z in neutral current exchange, one has sensitivity to the TQ gamma and TQZ couplings. And here is a function of center of mass energy on the left, on the right is a function of the integrated luminosity. One can study basically the constraints on the branching fractions here with 2 sigma uncertainty. And we see that for the LHeC, for instance, for the TQ gamma coupling, we expect sensitivity or basically a constraint up to 10 to the minus 4. And we can put this also into a more global picture. Here we have a comparison with LHeC prospects, the black line, the ILC and click prospects with the green line, and also the high Lumi LHC prospects with this violet line. And if we compare the different channels, we see that basically LHeC can contribute to some branching fractions TZZ and TZU is a comparable position like the high Lumi LHC. Sometimes it's better, sometimes of course the LHeC is much better than our electron-proton experiment. There's also of course the coupling to the Higgs. I think this was presented in Uta's talk in the Higgs session. So now I want to come to electro-weak physics. Electro-weak physics in this analysis on this proposal, we study mainly basically in the inclusive DAS cross-sections. On the right, I show the predicted cross-sections for the LHeC as a function of Q square. In fact, we measure double differentially later, but this is only as a function of Q square. And we compare with previous measurements at Hera. And we immediately see that we have 2 features. Of course, we go to much higher cross-section because of center of mass energy, and also we extend to much higher Q square. And we see that basically in the regime where electroweak effects become important, so it's about electroweak scheme 10 to the 4 GeV squared. Hera mainly ran out of statistics, and with LHeC we can really measure to a higher Q square with higher cross section. Also the higher integrated luminosity allows us to measure this tail, which is very important because in this tail we have a high sensitivity to the valence quarks. We know exactly the initial final state, and we have only very low QCD correction. So this allows us very precise measurements of electroweak effects in inclusive DAS cross sections. In the equations, these basically are put together in terms of structure functions. First of all, you have F2, XF3, and FL. These structure functions then compose the photon exchange in F2, the gamma Z interference term, but then also the axial and the vector coupling of the electron enters together with the normalization. And then we have the pure Z exchange terms where the couplings squared enter the calculations. Similarly, on the hadronic side, we have here the PDFs and the Wilson coefficients, and these quarks enter or couple to the Z, then through the vector and axial vector couplings, or through the interference term with the charge of the quarks. All calculations are performed in the on-shell scheme with 1-2 corrections. In on-shell scheme, the weak mixing angle is fixed with the two masses, the W and Z boson mass. The Z normalization is also given by this fixed quantity, including, of course, then the Z propagator. And the neutral current couplings, they include the one loop corrections, which are parameterized in these rho form factors and the kappa form factors. So the kappa essentially makes the weak mixing angle then become effective. And finally, basically, this whole model is composed in leading order from 3 parameters, which is alpha, mz, and w. And of course, the PDFs are free because this is the QCD initial state process. So what we now do to study electroweak effects, we have simulated a complete data set for neutral current, charge current, ds cross sections. It's a function of q squared x. So this is about, I think, several hundred of data points. These include a full set of experimental uncertainties on the electron measurements, on the polar angle measurement, on the hadronic final state measurement, and so on and so forth. And these pseudo data have also been used for the estimates for the PDF uncertainties. And Claire Gwennon talked about this in the QCD session on Tuesday, I think. And now we perform a complete QCD analysis. So we determine the PDFs. And on top, we also determine electroweak parameters. So in our prospects, already the PDF uncertainties are included in the following. So it's starting with one of the Born level parameters. This is in the on-shell scheme, the W boson mass. And here we expect that with LHeC, we can determine the W boson mass parameter with an uncertainty of 6 MeV, up to 12 MeV. In our study, we have performed basically 2 times 2 different assumptions. 2 assumptions on the electron beam energy, this is 50 or 60 GeV, so this has not yet been cited. And assumptions on the uncorrelated uncertainty, because we include the full systematic or the experimental uncertainty model in our prospect. The uncorrelated uncertainty is very important, but this is very, very difficult to estimate because this case is the resolution with the number of data points, with subtle details and calibrations, so on and so forth. And we have taken 2 different assumptions, 0.5% and 0.25%. This gives the difference between 6 MeV and 12 MeV. And if you want to interpret this measurement then in terms of physics, we see this is an indirect determination. So it's not quite the on-shell, it's the on-shell mass, but in the time-like regime, but at a much higher precision than basically the 2 tevatron others achieved until today. So this is a very precise consistency test of electroweak theory. An equally important quantity is the weak mixing angle. So for this assumption, we determine only the weak mixing angle in the on-shell scheme in the neutral current vector coupling. So this is basically what people consider as the weak mixing angle. All other appearances of this quantity in the form factors or in normalization constants are not included in our prospect here now. And then we have again these 4 prospects. The best has an uncertainty of 0.00015, which is of similar precision and basically the effective weak mixing angle from the LEP plus SLD combination. So these are 5 experiments taken together, many, many different measurements on these asymmetry observables. Here it's a single measurement of it, includes neutral current, charge current cross sections from a single experiment only, but they compare very well in size. If we compare this the standard model expectation of the prediction, this is not quite yet at the level that we can test the theory highly precisely, but of course we can compete with other measurements in the future. There's an important quantity that in DAS, this kappa factor, which makes basically the weak mixing angle to become effective is really effective, which means it has a Q-square dependence. So these are Z-pole measurements. Basically, this is just a single quantity, but here we have a Q-square dependence. Of course, we have to map the on-shell definition with the effective weak mixing angle. But very importantly, of course, we can then also measure the Q-square or the scale dependence of the effective weak mixing angle. This we have studied on the next slide. And if we all remember, basically, the running of the MS bar weak mixing and effective weak mixing angle, we see this blue curve. This includes the theory uncertainties. And the only experimental input, which is actually to some extent very valuable, is these few measurements at the Z-pole, but we hardly know about electroweak theory at any other scales. This is only from the theory, but we don't have any measurement. And with LHeC, we have made now this prospect where we determine the PDFs together with 12 values of sine square theta at different Q-square values. We really can measure the weak mixing angle or the running of the weak mixing angle in the regime from 25 up to 700 GeV, and this in a space-like regime. So this is basically in this regime where the weak mixing angle starts to rise again, but note that we are basically at minus Q squared, and this is plus Q squared. And one has to bring these two different regimes of momentum exchange together theoretically. But this is certainly a very unique measurement.
Excuse me, I think you only have 3 minutes left.
Okay, I hurry up. So then we have beyond three-level equations. Of course, we can study then in the rho T, the M top and the M Higgs dependence. The M Higgs dependence is not so important, but M top we can study, and more generally, we can also parameterize higher order corrections to the couplings, to the rho and kappa factors, or to the self-energy corrections of the W and the Z boson. If we study M top and MW, we see that we have a very similar sensitivity in the global electroweak fit. And also we test the same relation in the rho T term, like MT squared over MW squared. We are much better than LHeC, but yeah, quite similar as the global electroweak fit. So this gives us actually quite some promising prospect that we can test electroweak theory at the loop level. And if you then think about, again, on the couplings, we can test these rho parameters, the high order corrections, and the kappa parameters. And in a fit of rho and kappa together, we see again that basically we study the electroweak theory at the sub% level with a similar precision than LHeC. So here we have the LHeC uncertainties. But of course, again, at the Z pole, and we are at minus Q squared. Similarly, we can then study, of course, this K dependence of these kappa and these rho form factors. Kappa, again, is sine square theta. Rho is basically this normalization of the sets to the photon exchange in a large regime, also with percent or per mil precision. More generally, we can also then study the couplings. And here we are particularly sensitive to the light quark couplings, so the D quark couplings and the U quark couplings, because these are at high X in the PDFs to the Z. And this is something that has not been measured before with reasonable precision. And if we compare with our most conservative scenario, which is the yellow, tiny yellow contour here, and this is all of magnitude better than any previous measurements. So basically nowadays we don't know how the quarks couple to the Z, and finally we can make a very precise measurement here, also without any sign ambiguity, because we have these gamma set interference terms included. Then we have not only neutral current, but also charge current exchange. This is very important. Here, again, also very unique measurements can be done. First of all, these form factors or the high order factors can be measured or tested also in the sub% precision, and also its Q square dependence can be measured, because basically neutral current determines the normalization of all of the data, and then one can also determine the scale dependence of charge current interactions in a unique measurement, which was never done before. We have direct W and Z production. I skipped this probably because I want to talk about something more importantly, that at the high Lumi LHC, there are very, very promising prospects for the W boson mass measurement, for sine square theta, but also for many, many other standard model measurements. But most of them are limited by PDF uncertainties. And from the high Lumi LHC white paper, we know that basically the dominant uncertainty of the W boson mass is now the PDF uncertainties, and with high Lumi LHC PDFs, this becomes reduced by a small amount. But if we take the LHeC PDFs, then only we can reach a PDF uncertainty which is much smaller than basically the statistical or the experimental uncertainty of the measurement itself. So this is very importantly for science fiction. This is even more prominent because if one imposes the LHeC PDF, this reduces the uncertainty by a factor of 5 compared to a measurement from LHeC only. So this brings me to a summary. So we have 2 future projects on electron-proton collisions, both at the energy and both at the intensity frontier, how it's nowadays called. For top, there's a very rich program, in particular when there's single top measurements, but when also top-quark pair production cross-section can study a very, very large amount of top-quark quantities. I did not went into all details here. Electro-weak physics, we have just started in a paper, this was on archive 2 weeks ago, on IHEC. FCC, I have not discussed a lot, but this, of course, improves all these prospects quite a bit. In particular, what needs to be mentioned that many, many, many measurements are competitive with high-doom LHC and with DEP, but also one can test details of electroweak theory that have never been tested before. Also, for precision standard model measurements, the PDFs from high LHeC are very, very important, and only this will provide new precise measurements at the high-doom LHC. So, thank you. I was a bit over time, right? Please excuse.
Yeah, don't worry. Don't worry. We will still ask you questions though. So if you're hoping to avoid questions like that,
no, please go ahead.
I'm just joking. Are there any questions, please? Yes, I see a hand raised from Aram.
Hi, I just had a question on slide 12 when you were discussing the prospects for the W mass measurement. Yeah. I think you mentioned this, but just to make sure, so the uncertainties here, they only include the PDF uncertainties which are constrained in situ. So there is no experimental or other, let's say, QCD for the W boson production uncertainty.
So this is okay. It's a long way how to arrive at these uncertainties. So first of all, we have simulated data, and this inclusive neutral current and charge current data as a function of Q square and X. They include basically, let's go to page here, this page 5 or so. Basically this entire kinematic regime, you have basic data points all over the place. X and Q square for neutral current and charge current exchange. And then these data come together with a full set of systematic uncertainties. So on the electron measurement, energy scales, angles, background uncertainties, and all that. So this gives a fairly complete set of uncertainties. And I can also say that this is to some extent reliable because one made prospects in the same way for Hera, for the W boson mass, which were about, I think, 100 MeV. And this was exactly achieved with Hera data. So I am confident that this is reliable. So now this includes, we have this data with a full set of uncertainties, and now we perform a PDF determination and together with the electro-weak parameters at a time.
Okay, thank you. I see. And well, how much is how much is the improvement in the, let's say if you didn't constrain the PDF uncertainties in the
yes, you can artificially break this down. Here some numbers included into some uncertainty. So if you fix the PDFs, if you just consider them to come from heaven, then the uncertainty would be 8 MeV. So basically the other part then can be considered to some extent as an experimental uncertainty. So it's half. I mean, the trick essentially is that you go to basically at low energies, low Q square, you're entirely dominated by the photon. And the photon is very well known physically, and also this determines then the PDFs, mainly the gluon, and also the the valence, the C quarks. And if you then go to a higher scale, you measure precisely the shape of the neutral current and of the charge current cross sections, and the shape then is sensitive to the gamma Z interference, to the Z exchange terms. And the more you extend the measurement to higher Q square, the more you're sensitive to high X. And in high X, it's only then in the end the valence quarks, and there's no degree of freedom for the gluon left anymore. And this is why the PDFs do not become so important in this analysis.
Okay, thank you.
Okay, we now entered into the general discussions, but of course, questions to Daniel are still allowed. Just in case you have questions to other speakers that you didn't have a chance to ask, now would be a good time. So, are there any more questions to Daniel or to anyone? Remarks, comments? I don't see any hands raised. So just continuing the question of Aram, to put it in the perspective of LHC, then it seems like you can do much better than LHC for the W mass, but not for the top mass, especially in particular when we compare this against the direct measurements from kinematic from distributions of the top-quark decay products.
Yeah,
is this correct?
Certainly. Yeah, certainly.
Okay.
Certainly. I mean, this is. But one must come a little bit from a different perspective. So basically, electroweak tests are only done at the Z pole, and elsewhere we don't know anything about the electroweak theory. And if one has a measurements with per mil accuracy, of course, one tests or measures something that has never been measured before. This, of course, gives us at all confidence this theory does what we expect it to do. I mean, if you think about, top decays at the TV regime, we all impose electroweak corrections, but nobody ever has tested those corrections if they really are correct.
Right.
So just a purely theoretical assumption that we put into all these measurements nowadays.
Well, of course, it is an important. Of course, it is an important consistency test for sure.
Yeah. And I mean, what we see in these studies is basically that in many aspects we have a similar precision than LEP or with LHC. So basically, the main information is then if one goes into particular details, like to this Q square dependence that one can measure, into the charge current cross sections, or into the light quark couplings. If one looks, for instance, into whatever the electron couplings, of course, LEP can do much better. Or top direct measurements, or of course, if you want to have the W boson on shell, of course, Atlas and CMS can do much better. But other things, I mean, yeah, it's just the complementarity and the similar precision. I think this makes the whole project very interesting.
I completely agree. Thank you. There is a raised hand from Uta.
Yeah, thank you. So I wanted to dwell a little bit on this as well, because it's not only the complementarity between the different production types, but it's also that the electron-proton collisions, we would empower really our Atlas and CMS top measurements. Because currently when we are doing top measurements, which are exactly like this is just one example, but if you just think about our TD bar measurements that we are doing really very, very nicely with Atlas and CMS, there we have the PDF uncertainties and we have the alpha S uncertainties and we have the unknown top mass, to say so. So we have a couple of unknowns. And with the electron-proton external input, we would get rid of two of the unknowns at an extremely precise level. And this would then feed back in a much, much more precise top mass determination, I think, in proton-proton. Yeah? Like illustrated here also for our W mass. And where you see, by the way, that you have the different PDF families and they all don't agree. Yeah, this is, let's say, the true PDF uncertainty. I think it's still, let's say, very optimistically estimated at proton-proton. Yeah, so I think there's a big overall potential of the empowerment, including the luminosity uncertainty measurement, which we could do.
I mean, if you dig through the Run 2 papers, I mean, almost all standard model measurements are limited by modeling uncertainties or by PDF uncertainties. So it's very difficult to gain more from more luminosity without any external information. And what always comes too short, in my opinion, is partner shower modelings and such things. For two reasons. So basically in DAS, we have an initial state proton, and we can measure very, very precisely and very cleanly the hadronic final state, which is perfectly suited for all these partner shower and Monte Carlo tunings. This was never been done with Hera data because of the limitations in the Monte Carlo generators to get basically the structure function and all this physics correctly in for the hard matrix element. This has now been all solved. And once we have a precise measurement of the hadronic final state in DAS now, we can improve much better also these model uncertainties on the partner shower and hybridization, all that. This has just not been discussed much in the community, unfortunately.
Okay, thanks. I see, sorry, here's Christine speaking. Tomasz is just reconnecting, so I will convene for a bit. We have another question up from Jiří Tvita.
Yes, hello. Just a question. Many of us are interested also in the heavy ion run. Is that being planned?
Well, yes, there's a nuclear physics program, of course. That's electron mainly, or the other heavy ions. And I think the main focus there is on low X, low Q squared dynamics. And of course, about all the structure and the stuff from heavy ions, but I'm not a great expert on this. It's complementary to EIC. EIC looks into high X quantities because they just don't have the energy. But here one can test really low X physics. There was a talk from Nestor, I think, in the one of the parallel sessions. That the Henny Mentisari gave a talk on the heavy ion program.
Okay, thanks. I'll come back to that session.
Okay, thank you, Christine, for taking over while I recover from my Zoom crash. I hope I didn't lose the recording. But in any case, it seems like unless there are any further comments or questions, we are slowly running out of the time for the general discussion. So if there are no questions or comments, perhaps this would be a really good time to enter the Zoom screenshot competition. So if that's okay with you, would you be able to all enable your video streams while my colleagues try to take a couple of screenshots? Yeah, that looks great. Thank you.
Oh, amazing. So many faces. Good to see some people. Excellent. So we'll try some screenshots then. Just give me a second. Yes, just a moment. Yeah, actually very nice view of people. All right, some more best smiles. Yeah, and one more. 3, 2, 1. Great. Thank you a lot. And let's stay for the discussion.
Thank you, Jiří. Yes, so the topical discussion about electroweak precision just starts now. So please stay around, and I hand over control to my colleagues, to Christine and Aram, and thanks again to all the nice talks of today, and for the very interesting discussion. And let's go on discussing. Thank you very much.
Right, thanks, Thomas. Yeah, I think the idea was to discuss a bit today some of the discussion that already started in yesterday's session on the vector boson fusion production for Z boson, as far as the VBS measurements. In particular, we had some discussion for the QCD-induced ZJJ production, as it was shown during the Atlas talk. There seem to be some differences between different predictions, in particular between Sherpa and MC at NLO, and it was clear that, let's say, the description of the data in the control region, especially for Sherpa, was quite bad. We started some discussion there, but I was wondering if we could maybe, if someone from Atlas knows, if we could get a little bit more information about the settings and the configurations used for these predictions, especially for Sherpa. There was a question from Marco if some of these color flow predictions settings, if there were perhaps some uncertainties that needed to be included in the Sherpa predictions. I think we just have an open discussion, so anyone can just unmute and talk. There is no need to raise the hand, but if anyone has any comments in that direction, please go ahead.
Aram, can you just clarify there whether you're on about the QCD sample or the electro-weak sample, because you mentioned color flow settings?
So I think we can discuss both. So let me see if I can share the slides from Thursday. Just give me 1 second. Yeah, I think let's start from here. All right, so if people can see the slides, well, first let's just give me 1 second. Yeah, I think we started from this slide, on slide 4. If we look at for example, the QCD-induced ZJJ production, the differences here between Sherpa and MC at NLO. Well, one question is how many jets at matrix element level are included for Sherpa here, and also for MC at NLO?
So Sherpa on this analysis is up to 2 jets NLO. Plus 3 or 4 jets at leading order. The MagGraph sample that's at NLO accuracy is up to 2 jets at NLO. So that gives you the 3rd jet at leading order, but then there's nothing on top of that. That's merged using FXFX. And then the leading order sample is of MagGraph is up to 4 jets leading order.
Okay.
This is Marco, sorry. Do you do anything for the normalization of this sample? Like you normalize the leading order to the next leading order cross section, or anything like that?
Yeah, so you can find the details of this in the paper that's linked at the top, but basically we normalize in the inclusive Z region to a high order calculation and NLO. And then if you go in, when we studied the difference of these generators, because exactly these types of differences came up in the review, and what we find is that in the inclusive phase space, even after all of our selections, things are in good agreement. I think even in the 2-jet phase space, when you don't go to high MJJ, things are in good agreement. But these differences really arise when you go to high MJJ.
And what are the uncertainties that you quote? You said it yesterday, but I can't remember.
So I'm 98% sure that the middle column here is experimental uncertainties, and then the 3rd column is theoretical uncertainties, where we have them.
For example, why Sherpa is an uncertainty of like 5,000?
That's just what comes out of varying. So these uncertainties are much smaller in a normal 2-jet phase space, right? But when just in the samples that we have, when you vary in the renormalization, the factorization scales, we have 7-point systematics here, like 7
So
variations.
this is you have like a 30% uncertainty due to renormalization and factorization scale.
In this,
and in the case of
yes,
and in the case of ancient NLO, this is more 10% uncertainty, give or take.
In this phase space, yes. Sherpa has a bigger problem going to forward jets, and this is even the NLO problem. This is not really necessarily even an NLO problem. We've seen all of these bad modeling in run 1 with leading order generators at high MJJ with Sherpa. But yeah, this is what comes out. So I mean, if you look at the size of these uncertainties, they agree.
I was wondering if these were like statistical uncertainties due to the fact that this phase space region is difficult to fill. But I don't know what to say then.
No, we have more statistics in the Monte Carlo than we have in the data in these regions, and this is scale variations in the sample. So the MC uncertainties are included, but they're small in comparison. The stats ones.
But sorry, just to Andrew, I think you mentioned it. So because let's say formally speaking, the accuracy of the Sherpa here and then the MC8 and NLO are the same, no, next to leading order. So, and if I understood correctly, the theory uncertainty here comes mainly from the renormalization and factorization scale variations. So is it kind of one naively would expect not to see large differences in the theory uncertainty here between Sherpa and MC8 and NLO?
So in an inclusive 2-jet phase space, that's exactly true. They're very similar at the 10% level. The difference is that Sherpa explodes its theoretical uncertainty as you go to large rapidity separation and large MJJ.
Okay.
Mm-hmm. Unless this is also related to the problem of the color flows, but I don't know if this problem is also there for the QCD sample.
I think we'd have to refer that to Sherpa. My understanding was that it wasn't there when we had all of the color flow problems in the first place with the electro-weak samples. We spent a lot of time discussing with the Sherpa authors, and it's essentially the problems with the color flow are that Sherpa was assigning the wrong color flow, which is essentially assigned based on QCD principles, right? So it should be right in the strong sample, right?
It depends, because when you go at the very large invariant mass, I mean, if it may be that it works well when you are inclusive, but if the problem is there when you go at large invariant mass, you may have other color flows dominating. So check this. I'm not a Sherpa author, but I would suggest to check this issue.
I mean, I don't disagree. I think that's a good idea. We've discussed this with Frank Krause in the past. Like I say, this showed up in run 1 with leading order, right? When with Sherpa 1.4, which is a very different generator, and the suspicion at the time is that how Sherpa is choosing the scales, right, for very well separated jets is where the issue might be, right? That's what Frank said a few years ago, right? But yes, I think that this needs quite a bit of investigation.
And for the electro-weak differences that we see here between, let's say, I mean, it seems like, yeah, between the Sherpa predictions and the other one, do you have some comments about those? Is this, you said you were in contact with the Sherpa authors for the electro-weak case.
Yeah, so this is Sherpa 2.2. It has a famous color flow bug. Now, the way that color flow bug works is that you end up with a reduced cross section, right? So you can see this in the differential cross sections that we measure. We have pretty similar shapes, but much smaller cross section, right? This is fixed for the advent of Sherpa 3 when that gets released, right? And I leave it to Sherpa authors to make a more concrete statement on this, but I believe that the Sherpa sample will not have this problem with Sherpa 3. And this is true across the board for all electroweak samples produced with Sherpa 2.2.
Okay, and so this is precisely the same thing that happens, for example, for the same sign WW measurement with Atlas. With Atlas, that also.
Yeah, it arises, if I understand correctly, when you do a merging between the 2-jet and the 3-jet matrix element. That's where it comes in. So if you actually generated just the standard sample without the 3rd jet, I don't think it's as bad then.
Yes, it is.
Is it? Oh, okay.
So the issue is in the interfacing with the parton shower, in the matching with the parton shower, is my understanding. So there is, yeah, it's the interfacing with the matching with the parton shower, and then you have different effects depending on how many legs you include. So I'm not sure what this is. Assume you have multi-leg configuration here, right?
Yep.
In Z, and the same is true for same sign WW. But when you go, for example, to WZ VBS, we don't have a multi-leg setting. So then, if you don't have a multi-leg setting, you get just a suppressed emission of central jets, essentially. But the cross section is not far off, so it's an effect on kinematic distributions.
Okay. Yeah.
When you include additional partons in the matrix element, then you mitigate these issues that you have in the kinematic distributions to some extent. So you get the central jet emissions more correct, but then this leads to some cancellations of you know, it's all about the logs and what I'm not an expert on this, but you mitigate the description of the differential distributions, in particular on the extra jet emissions, but you get a systematic underprediction of the cross section. So this is kind of the feeling that I got for this color flow bug.
Okay, any other comments on this?
Can I ask a question in somewhat of a tangential direction? I'd kind of like to understand more the impact on the measurement than the kind of overall differences of the generators. So as I understand it, the uncertainty that you assign to the modeling of both the QCD background and the electroweak signal comes from actually taking a different central value for the templates that you use for these processes in the fit. Is that right?
It's one of the uncertainties that we do, yeah. Right. We vary the generator that goes into the signal and control region fit. That's if you go up the slide, that's the best one to show. Yeah.
So you really propagate that all the way through the fit. You get a different signal strength and a different, you know, and you take the different signal strength that you get as part of the uncertainty.
Yeah.
How big of an impact is that? How does it compare to just, you know, taking the central value as what you think is perhaps the best prediction, and then having, you know, an uncertainty band with some log normal constraint in the fit?
So what would the uncertainty band come from then? So this is one of the methods. We also vary factorization and renormalization scales and repeat, right? So we do it with different templates, we do it with different variations of each generator. But yeah, so what would we do instead of using a different template? And then what would you be idea? How do you assign the uncertainty, right?
Well, I mean, I don't know that there is a correct answer, but I mean, you certainly sacrifice some degree of the statistical interpretation of the measurement when you take an approach like this. I mean, of course, theoretical uncertainties are not they don't really follow the statistical interpretation that we would like to have of some, best predicted value and a decreasing amount of confidence in that value as you move farther and farther away, and therefore a logical reason to have, a constraint pulling it back towards the central value in the fit. But
so sorry, I misunderstood your question. What you're saying is what's the difference between propagating it through independently and including it as something that you can profile in the fit? That's your question.
Yes, exactly.
I don't know. We worry a lot inside Atlas about profiling things like 2-point systematics, right? So had we chosen to go down that route and we'd ended up with a profiling of that uncertainty, then we would have faced all sorts of difficult questions about whether we over-profile it. So either it wouldn't profile it and you end up with the same result, right? Or you would profile it, right? In which case, for a 2-point systematic, like different choice of generator, the question would be, how do you know that that's valid, right? And so I don't actually know the answer to your question, right? But it would either come out the same size or it would be heavily profiled, and then you would run into a problem of how do you know that this arbitrary? I mean, sometimes 2-point systematics. I mean, we have a 3-point systematic here. We use 3 generators, right? But still, the point remains, right? That what would if you did constrain it that much? How much do you trust that constraint, right? So it's really a conservative option.
But then I don't quite understand how I'm left with a statistical interpretation of the uncertainty band. I mean, if the uncertainty band is kind of a flat, I mean, there's essentially a flat, there's a flat confidence interval in some sense. And you say, I have no preference between any of these points. I just expand my uncertainty band to capture all of them. So why should I expect the, central value to have more meaning than the plus or minus 1 sigma?
We don't, but that's the nature of the theoretical uncertainty, I think, right? Is that these things, the scale variations, for example, right, are not Gaussian, not meant to reflect Gaussian distributions. It's just how we choose to use them afterwards in our fits. We take them to be Gaussian approximations, but there's a lot of arguments, right, that these could be top-hat type uncertainties. I think you report what you have, and then there is always an issue with theory uncertainties as to what they mean.
So what fraction of the systematic uncertainty comes from these sources, from theoretical sources, on just the electroweak cross section?
So from the background process, it is dominant, right? That's the dominant source of uncertainty, has been in most of our measurements actually of VBFV and also VBS. The electroweak difference is entirely minimal, right? So which is good. We don't depend on the thing we try and measure.
But the in the final number that you report for the electroweak cross section, I'm scanning through the paper trying to find it.
So if you scroll down maybe to the next slide, whoever's sharing, I think that, so I'm pretty sure I saw an uncertainty band somewhere, right?
Yeah, 37.4 plus or minus 3.5 stat, 5.5 cyst. So of the 5.5 cyst, what fraction is theoretical?
So you can see, and you're focusing on the integrated cross section now with that number, is that right?
Yeah.
Right. It's probably more instructive to look at what's being shared here. This plot in the bottom left of slide 8, right? Basically, you've got these are all added in quadrature on top of each other. These bands. So you've look at the first bin of MJJ, which is dominating that. You've got a 10% experimental uncertainty. Okay, bit of electroweak theory in there as well, and then it increases to about 16% with the strong modeling, but this is added in quadrature, right? So this is a large increase. It will be about 11-12%, right, in that bin, right? And then you've got the statistical uncertainty on top, right? So it's quite large, right?
Okay, thanks.
Okay, any other questions related to this? there was one more question during the discussion. I mean, not related to this modeling uncertainties, but rather to the dimension 6 operator limits. There was a question about if this included any. I mean, if there were, if the unitarity effects were included in the limits, or let's say the possible violation of the unitarity was ignored in these interpretations. I don't know if Andrew, perhaps you know the answer to this.
I do know the answer. They weren't, unitarity effects weren't considered, right?
Okay.
But so Philip asked me this yesterday. I couldn't make the session yesterday, I apologize, but Philip asked me on Skype, and the thing to realize is that when we're actually doing the interpretation, we're using the delta phi JJ variable, and what we're exploiting there, you see that we're sensitive to the linear term in the EFT, right? Not the quadratic term in the EFT. So we're entirely driven by the linear term between increases between positive and negative interference, right, across that spectrum. It's difficult to imagine that we have a really big unitarity problem here, right? Because we're entirely driven by the linear term, which will not grow as fast, right? That said, we can always test it, right? These are unfolded data, right? We can test it. It's maybe something interesting. Provide some feedback on this. Right?
Yeah. No, I think that's good. These are unfolded data. Yeah, so this can be.
I mean to add, after some discussions with Céline Desgrandes on the dimension 6 in QQ to WW production. Okay, this is a little bit different process, and then it is of course very process dependent. But there is specific processes where the dimension 6 will not run into unitarity trouble. And as I said, for example, the QQ to WW. So not the scattering, but the normal diboson production is one of them. So it might be easily applicable here as well, though I'm not entirely sure.
Do we have any other comments on this? Okay, I think so. One thing, if there are no comments on the ZJJ measurements, there is one question I had for the VBS measurements. I know that there has been quite a bit of effort in the LHeC electro-weak working group and also VBS scan to compare the, let's say, the different predictions for the electro-weak productions that were used by Atlas and CMS for the measurements in the past. I mean, comparing, for example, Sherpa versus MC8 and NLO CMS, also PowerX samples. I was wondering if someone can briefly summarize the situation there of what is the understanding of the let's say the agreement between the predictions that the two collaborations are using.
So I don't know whether CMS might want to comment, but so currently these comparisons are only available for the same sign WW. They're currently in CMS circulation. They have been signed off basically by Atlas. And I will have to remind myself, but in principle, in principle, the main comparisons are between, let's say, the main predictions that were used by Atlas and CMS. They are surprisingly relatively similar. And Yes. So it's not really so you can see there's a broad range of predictions, and the let's say the differential distributions also look a little bit different, but none of them are outrageously different. It looked a little bit like for the MG5 in for the CMS sample, there was some lucky cancellations, let's call it, between the third jet PT spectrum and the cross section. But yeah, I'm sorry, I cannot say anymore. It's been a long time since I looked at the plots.
Yeah, actually, the plots were approved yesterday in CMS, so we are finalizing the making more beautiful plots and so on. I mean, there are a few requests, but physics-wise, it was approved actually yesterday. So finally, this will be out officially from the CMS side, and I'm sorry for the delay.
So the idea, this would be Atlas plus CMS conference.
Yes. So they I mean, in the labels they appear Atlas, CMS, and so on. So, but formally they needed to be approved from both experiments, and for reasons that I was not aware, it took a long time for CMS. So.
I mean, it should be added that this is the first time that this was done for the dye boson measurements. It has been done before for the top group, but because it was, I mean, the standard model group is sort of a different group, and then because there was not yet a procedure, I think it also took a while to iterate on these things and establish how to do them. There were quite a few things that had to be investigated in the samples and so on, which also took a bit longer. So hopefully the next comparisons, and maybe there will be some ZJJ comparisons as well in the future, might go a bit faster.
Yes. I mean, I think the main problem, at least in CMS, is that there were two groups in principle that could have taken the ownership, and none of them wanted to take it at the end. So they thought that this was someone else. But I think, well, maybe it helps the fact that I was kind of interested in being approved. So now I push for it. But yeah, I'm happy that I think now there is a procedure. So at least from the SMP side, we know how to do it. So.
Okay, sounds good. I think we kind of allocated until we have until 1:30 for the discussion. But if people have anything else related to this to bring up, please go ahead. Any other comments or discussion topics? Okay, if not, let's see if there's something in chat. Yeah, if not, thanks again, everyone. Thank you for the speakers today, and this is the last parallel session. Unless my co-conveners have anything else to add, we can close the session.
Yeah, I think just in general, we are very happy that people connected, and thanks a lot for taking part in all the discussions, even the topical discussions after the long sessions. And thank you a lot for participating, and enjoy the rest of the conference, which officially starts next week. And enjoy the plenary sessions.
Thank you, everyone. Bye-bye.
Yeah, thank you all.
Thanks.
Bye-bye.
Thank you.
Bye-bye.